Hello there, and welcome to Physics with William, where we take complicated ideas, give them a comfortable chair, and let them explain themselves without shouting. Tonight, we are looking at a result that sounds wrong the first time you hear it. Light, the same thing that warms your face in the sun and heats a dark car on a bright afternoon, can be used to cool atoms. That may seem like saying a hairdryer can make ice, or that an oven can help a cup of tea become colder. Light carries energy. When matter absorbs that energy, we usually expect its temperature to rise. This is why sunlight warms the ground, why a lamp can heat a small surface, and why standing too close to a strong studio light can make you reconsider every decision that brought you there. Yet inside carefully controlled laboratories, physicists aim laser beams at clouds of atoms and make those atoms move more slowly. Since the temperature of a gas is closely connected to the motion of its particles, slower atoms mean a colder gas. Before we go any further, where are you listening from tonight? And is the room around you warm, cool, or somewhere in that uncertain range where one foot wants the blanket and the other strongly disagrees? Temperature is such a familiar part of daily life that we rarely stop to ask what it means on a smaller scale. We feel warmth through our skin. We read numbers from thermostats. We wait for food to cool and complain when the shower changes temperature without warning. At the level of atoms, however, temperature is not a substance stored inside an object. It is a way of describing motion. In a warm gas, atoms move quickly in many directions. They collide, change course, and spread through the space available to them. In a colder gas, their motion is slower. The atoms still move unless we reach conditions that are extraordinarily close to the lowest possible temperature, but they do so with less speed and less disorderly rushing about. Cooling atoms therefore means removing some of their motion. It means finding a way to reduce their speed without simply placing them in a colder box and hoping for the best. That is where light enters the story. If this quiet exploration helps you settle down, or if you enjoy finding out why nature often ignores what seems obvious, you can leave a like and subscribe to the channel. It helps more curious listeners find their way here, including those who may have searched for one simple answer and somehow ended up thinking about lasers at bedtime. Now, with the room a little quieter and the question clearly in front of us, let us look at why light can cool atoms, even though light is usually associated with heating. The apparent contradiction comes from treating every interaction between light and matter as though it were the same. It is not. Light can be absorbed, reflected, scattered, transmitted, or released again. The result depends on the material, the colour of the light, the structure of the atoms, the direction in which everything is moving, and the conditions around the experiment. A beam of sunlight striking pavement involves an enormous range of colours and a dense solid containing a great many particles. A carefully tuned laser meeting a thin cloud of selected atoms is a very different situation. A laser is useful because its light can be controlled with remarkable precision. The beam can be given a narrow range of colour, its direction can be fixed, its intensity can be adjusted. Several beams can be arranged to meet the atoms from different sides. Most importantly, the light can be tuned so that it interacts strongly with atoms moving in particular directions and only weakly with others. This selectivity is the key. The laser is not acting like a general blast of heat. It is acting more like a very patient traffic officer that responds most strongly to atoms moving the wrong way. The comparison is not perfect, because atoms are less cooperative than drivers and considerably harder to issue a ticket to, but it gives us a useful starting point. To see why motion matters, imagine a cloud of atoms released into an empty chamber. The chamber contains almost no air, because ordinary air molecules would collide with the atoms and disturb the experiment. The atoms move in all directions. Some travel left, some right, some upward, some downward, and many at angles that are inconvenient to describe without pointing at the ceiling. From our ordinary human perspective, the cloud may look nearly still. On the atomic scale, it is busy. Now imagine shining laser light toward that cloud. Light can transfer momentum when atoms absorb it. Momentum is simply a measure connected to motion. You do not need a heavy object for momentum to matter. Light has no rest mass, but it still carries momentum and can give a small push to an atom. The push from one particle of light is tiny. Repeated many thousands or millions of times, however, tiny pushes become useful. This already explains part of the puzzle. Light does not only deliver energy that can become heat, it can also apply force. Solar sails are based on the same broad fact. Light from the sun can push on a reflective surface. The pressure is very small, but in space there is little resistance, so a gentle push can continue to change a spacecraft's motion. In the laboratory, physicists use the pushes from laser light on a much smaller target. Instead of moving a sail, they change the motion of individual atoms. Of course, simply pushing atoms is not the same as cooling them. If the laser pushes all the atoms in one direction, the entire cloud may drift across the chamber while remaining just as warm as before. That would be transportation, not refrigeration. It might be useful, but it would not answer our question. Cooling requires the random motion within the cloud to become smaller. Fast atoms need to lose speed, and the pushes need to oppose their movement rather than merely send everyone on a group outing toward the nearest wall. The solution depends on the fact that atoms do not absorb every colour of light equally. Each kind of atom has a set of specific changes it can make between internal energy states. Light with the right colour can trigger one of those changes. Light with a colour that is too far away from the required value usually passes by with little effect. Physicists can therefore choose a laser colour close to the value that an atom prefers, while setting it slightly away from an exact match. Why choose a colour that is slightly wrong? Because moving atoms do not see light in quite the same way that stationary atoms do. Motion changes the apparent colour of the light from the atom's point of view. This is related to the Doppler effect, the same familiar effect that changes the pitch of a siren as an emergency vehicle approaches and then moves away. The sound waves do not change because the driver has reached a special button marked Dramatic Exit. The change comes from relative motion between the source and the listener. Light behaves differently from sound in important ways, but relative motion can still shift the frequency that an atom experiences. An atom moving toward a laser beam can see the light shifted closer to the colour it readily absorbs. An atom moving away can see it shifted farther from that useful colour. By tuning the laser carefully, physicists arrange matters so that atoms moving toward a beam are more likely to absorb its light. When such an atom absorbs light, it receives a push opposite to its motion. The atom was moving toward the beam, while the light was travelling toward the atom. The transfer of momentum slows the atom down. A short time later, the atom releases light again and returns to its earlier internal state. The released light goes in a largely random direction. That random emission gives the atom another small push. But because the direction varies from one event to the next, those pushes mostly average out over many repetitions. The slowing pushes from the incoming laser, however, are arranged in a preferred direction. Their effect builds. That is the basic reason light can cool atoms. The laser is tuned and positioned so that atoms moving toward it absorb more light and receive more pushes against their motion. With beams coming from opposite directions, atoms moving either way can be slowed. Add beams along several directions, and the cloud can be cooled throughout three-dimensional space. It is worth pausing over how unusual this control really is. A room heater does not inspect air molecules and choose only the ones moving toward it. Sunlight does not politely sort atoms by direction before interacting with them. Laser cooling works because the light is narrow, stable, and carefully chosen, and because the atoms have specific responses that physicists can predict. The process is less like placing something in a freezer and more like correcting motion one small event at a time. The atoms are not aware of this arrangement naturally. There is no tiny committee inside the cloud deciding to slow down for scientific progress. Each absorption and emission follows the rules of quantum physics. The cooling emerges from a large number of these events, all shaped by the laser frequency and the geometry of the beams. This also means the phrase laser cooling can be misleading if we picture a cold beam. The laser itself does not need to be cold. The equipment may produce heat, use electricity, and require its own cooling systems. What matters is the way the laser light exchanges momentum and energy with the selected atoms. The cooling belongs to the atomic motion, not to the personality of the machine. You might wonder whether the atom gains energy when it absorbs light. It does. For a brief interval, the atom occupies a higher internal energy state. Then it releases light and returns to a lower state. The important detail is that the emitted light can carry away slightly more energy than the atom received from the laser beam. That extra amount comes from the atom's motion. Repeated many times, the atom gives up kinetic energy, which means it slows down. Nothing is being created from nowhere, and no law of energy conservation is being avoided. The laser system is not performing a clever trick against nature. It is using the allowed exchanges between light and atoms so that motion is gradually transferred away. Energy leaves in the scattered light, while the atomic cloud becomes colder. The scale of the result can be astonishing. Ordinary room temperature feels calm to us, but atoms in a room temperature gas are moving at hundreds of meters per second. That is faster than a passenger aircraft and achieved without luggage, boarding passes, or a delay announcement. Laser cooling can reduce atomic speeds dramatically, sometimes until they are moving at speeds that fit much more comfortably into human imagination. At those low temperatures, physicists can observe behavior that is usually hidden by thermal motion. Atoms can be trapped for longer periods. Their internal transitions can be measured more precisely. Quantum effects that would normally be blurred become visible. Atomic clocks become more accurate. Sensors become more sensitive. Experiments can test basic physical laws with extraordinary care. The cooling is not merely a technical preparation step, although it often begins that way. It opens a different regime of nature. When atoms are hot and fast, they collide often and move through the apparatus quickly. Their signals are broadened because different atoms see light differently depending on their motion. When the atoms slow down, measurements become cleaner. The laboratory gains time to ask more detailed questions. Consider an atomic clock. It does not work by watching a tiny hand sweep around a tiny face. It uses a precise transition inside atoms as a reference. If the atoms are moving quickly, their motion shifts and broadens the light they absorb, making the reference less sharp. Cooling the atoms reduces these disturbances. The clock can then compare frequencies with greater precision. The result affects technologies that depend on accurate timing, including navigation and communication. Cold atoms also help physicists measure gravity and acceleration. Matter has wave-like properties at the quantum level. When atoms are cooled, those properties become easier to control and observe. Carefully prepared atomic waves can be split, guided along different paths, and recombined. Tiny differences caused by gravity or motion then appear in the final signal. The same broad idea that begins with slowing atoms using light leads toward instruments capable of detecting remarkably small effects. There are limits, of course. Laser cooling does not continue forever with no complications. The random recoil from emitted light prevents perfect stillness. At very low temperatures, those small random pushes become significant. The internal structure of real atoms can make the process more complicated than the simplest explanation suggests. Some atoms are easier to cool than others because their energy levels offer convenient transitions that can repeat many times without the atoms slipping into a state the laser cannot reach. Researchers developed additional techniques to go below the limits of basic laser cooling. Some use patterns of light and the internal states of atoms to remove more motion. Others use magnetic fields to trap the atoms. Evaporative cooling can remove the fastest atoms from a trapped gas, allowing the remaining atoms to settle at a lower temperature. That method resembles the way steam carries energetic molecules away from a hot drink, although the laboratory version is more controlled and usually involves fewer biscuits. Still, the first surprise remains the most important one for our discussion. Light is not automatically heating or cooling. The outcome depends on how energy and momentum are exchanged. Broad, uncontrolled absorption usually adds random motion and raises temperature. Carefully selected absorption can oppose motion and reduce it. The same general agent, light, can produce opposite results because the conditions are different. We see similar situations elsewhere in physics. Friction often slows an object, but a moving surface can also speed it up. Air can cool skin through evaporation, yet compressed air can become hot. Water can put out many fires, but under certain conditions it can create serious hazards. Nature rarely promises that one thing will always have one simple effect. Context is not an annoying detail added after the explanation. Context is the explanation. Laser cooling became possible only when several areas of physics came together. Scientists needed a detailed understanding of atomic energy levels. They needed lasers stable enough to target narrow transitions. They needed vacuum technology to isolate atoms from unwanted collisions. They needed magnetic fields and optical components that could guide, shape, and balance the beams. They also needed the patience to adjust equipment whose correct setting might differ from the wrong setting by an amount too small for ordinary senses to notice. A typical experiment does not look dramatic in the way a rocket launch does. There may be optical tables covered with mirrors, lenses, cables, metal chambers, detectors, and devices that seem determined to catch a sleeve whenever someone leans too close. Laser beams travel between components, often at heights chosen for optical convenience rather than human comfort. Inside a vacuum chamber, a small cloud of atoms may glow faintly as it scatters light. That glow can be a sign that cooling is taking place. The atoms absorb laser light and emit it in random directions. Some of that emitted light reaches a camera. To the viewer, the cloud may appear as a small bright spot suspended in the chamber. It looks simple. Behind that spot lies a carefully balanced interaction between motion, frequency, quantum states, magnetic fields, and repeated transfers of momentum. There is something satisfying about the fact that cooling can be seen as light. We usually associate a glow with heat. A fire glows, hot metal glows, stars glow because they are extremely hot. In a laser cooling experiment, the visible light may come from atoms becoming slower. The glow is not proof that they are warm. It is evidence that they are repeatedly absorbing and releasing light, while the arrangement removes motion from the cloud. This is also why everyday intuition can struggle with atomic physics. Our intuition was built from objects large enough to touch and temperatures common enough to survive. We know what happens when sunlight reaches skin or when a pan sits on a stove. We do not naturally know what happens when a narrow laser frequency is tuned just below an atomic transition inside a vacuum chamber. There was no strong evolutionary reason for our ancestors to develop an instinct for that situation. Fortunately, physics does not require the right instinct at the beginning. It asks us to define what is happening, identify the exchanges, and follow the consequences. Temperature describes motion. Light carries momentum. Atoms absorb selected frequencies. Motion changes the frequency they experience. Arrange the light so that moving atoms absorb pushes against their direction, and the cloud slows down. That explanation is compact, but every sentence inside it contains another question. How can something with no rest mass push an atom? Why do atoms absorb only particular colors? How does motion change the light from the atom's perspective? Why does random emission not undo the cooling? How can beams from several directions create a region where atoms feel as though they are moving through thick syrup? Those questions will take us deeper into the mechanism, but there is no need to hurry. For now, picture a single atom crossing a quiet vacuum chamber. It is moving quickly, though no eye could follow it directly. Ahead of it, a laser beam travels in the opposite direction. The light has been chosen so that the moving atom is especially likely to notice it. One particle of light is absorbed. A tiny push follows. The atom continues, but a little more slowly than before. The event repeats. Another absorption, another push, another small loss of motion. Light is released in changing directions, carrying energy away. Around the atom, other beams are waiting for motion along other paths. What appears at first to be a contradiction begins to look like a controlled exchange. The light does not cool by being cold. It cools by knowing, through the rules of motion and atomic response, which atoms to push and when. To understand that push properly, we need to look more closely at what light carries, what happens during absorption, and why a collection of nearly weightless particles can act like a brake on an atom moving through empty space. To understand that push properly, begin with the simplest possible picture. An atom is moving through an almost empty chamber, and a beam of laser light is travelling toward it. Nothing appears to touch the atom in the ordinary sense. There is no paddle, no gust of air, and no tiny hand reaching out from the beam. Even so, the atom can slow down. The reason is that light carries momentum, and when an atom absorbs light, some of that momentum is transferred. Momentum is usually introduced with moving objects that have mass. A rolling ball has momentum. A moving car has much more. If either one strikes something, its motion can be passed along. Light is different because it has no rest mass, but it still carries energy and momentum. That may sound like a technical exception added to make the story work, but it is a measured feature of light. Light can push on matter. The push is usually so small that everyday objects do not respond in any obvious way, yet atoms are light enough for the effect to become useful. A single atom is extremely small and extremely light. A single particle of light delivers only a tiny push, but the change in the atom's motion is not zero. If the atom absorbs one particle of light travelling from the left, the atom receives a small push toward the right. If it absorbs another from the same direction, it receives another push. Repeat this many times, and the effect builds. The particle of light involved in such an interaction is called a photon. A photon is not a little glowing marble, though that picture can be helpful for keeping track of direction and momentum. Light also behaves like a wave, and both descriptions are needed in physics. For the moment, thinking in terms of photons makes the transfer easier to follow. Each photon carries a specific amount of energy and a specific amount of momentum related to the colour of the light. When the photon reaches the atom, absorption can occur only if the atom is able to take in that particular amount of energy. Atoms are not like buckets that accept any amount poured into them. Their electrons can occupy only certain allowed energy states. If the energy of the incoming light matches the difference between two suitable states, the atom can absorb the photon. One of its electrons then moves into a higher energy state. This higher state does not usually last long. After a very short time, the atom releases a photon and returns to a lower state. The released photon carries away energy and momentum. At first, this may seem to ruin the whole cooling process. If absorption pushes the atom one way and emission pushes it another, perhaps the effects simply cancel. They do not cancel in the way that matters. The photon from the laser arrives from a controlled direction. If the beam travels from left to right, every photon absorbed from that beam brings momentum from left to right. The absorption pushes are therefore organised. Spontaneous emission is different. The atom can release the new photon in many possible directions. One emission may push the atom slightly left. Another may push it upward. The next may push it at an angle. Over a large number of events, these random recoil pushes tend to average out. Imagine standing in a room while someone repeatedly rolls tennis balls toward you from one doorway. Each ball pushes you in the same general direction when you catch it. After every catch, you throw the ball away without looking. Some throws go left, some right, some forward, and some backward. The throws make you wobble, but they do not create a steady push in one direction. The incoming balls do. An atom behaves on a much smaller scale, and the quantum details are more precise than this comparison, but the pattern is similar. Directed absorption produces a steady average force. Random emission adds small fluctuations. This average force is often called radiation pressure. The name can make it sound like a broad pressure spread over a surface as sunlight presses on a sail. At the level of one atom, it is better to picture a rapid series of individual momentum transfers. How rapid can the series become? Very rapid indeed. If the laser frequency is chosen correctly, and the atom can return to its original state after each emission, the cycle can repeat millions of times in a second. The atom absorbs, emits, absorbs again, and continues doing so while it remains in the beam. Each cycle changes its motion by a tiny amount. Millions of tiny changes can produce a noticeable slowing force. This repeated cycle depends on having an atomic transition that can be used over and over. Suppose the atom absorbs light, releases a photon, and returns to the same state where it began. The laser can then excite it again. This is known as a cycling transition. It is extremely valuable for laser cooling because the process must repeat many times. Real atoms often have several lower energy states, however. After emission, an atom may sometimes fall into a state that the cooling laser does not address. Once that happens, the atom becomes dark to the beam. It is still present, but it no longer absorbs the cooling light. Physicists solve this by adding another laser, often called a repumping laser, which returns the atom to the state used by the main cooling cycle. The word repumping may suggest a mechanic trying to restart a stubborn machine, which is not entirely unfair. The atom has wandered into the wrong internal state, and the extra light brings it back into the useful sequence. Without this help, many common laser cooling experiments would lose atoms from the cycle too quickly. Now consider the size of each push. The change from one photon is small, but an atom may need to lose a great deal of speed. An atom travelling at hundreds of meters per second cannot be brought nearly to rest by one or two interactions. It may need tens of thousands of absorptions, or more, depending on the atom and its initial motion. The slowing distance can still be manageable because the cycles occur so quickly. In some experiments, a beam of atoms enters long apparatus and is slowed as it travels. In others, atoms are first captured and then cooled in a small region. The exact arrangement depends on the element, the available lasers, and what the researchers want to do next. It is important to separate two effects that can look similar. A beam of light can change the average motion of an entire group of atoms, and it can also reduce the spread of their random motion. The first effect is acceleration. The second is cooling. Suppose every atom in a cloud is moving randomly, but a laser pushes all of them to the right with nearly the same force. The cloud begins drifting right. Its center moves, yet the atoms may remain just as disordered relative to one another. Their temperature may not decrease. A moving cloud can still be cold, and a stationary cloud can still be hot. Temperature is linked to motion relative to the average motion of the group, not simply to whether the group is travelling through the laboratory. This distinction matters because radiation pressure alone does not guarantee cooling. To cool, the light must push differently on atoms moving in different directions or at different speeds. Fast atoms need a stronger slowing effect than slow atoms. Atoms moving left need to be pushed right, while atoms moving right need to be pushed left. A single unchanging beam cannot handle all of that by itself. The first step is to use two beams travelling in opposite directions. Place one laser beam on the left side of the atomic cloud and aim it to the right. Place another on the right and aim it to the left. If both beams had exactly the right frequency for stationary atoms, a stationary atom would absorb from both sides and receive pushes that roughly balance. An atom moving left would also encounter both beams, but without another effect there would be no strong reason for it to absorb more from the beam opposing its motion. That other effect is the change in apparent frequency caused by motion. Before reaching it, though, it helps to understand how carefully tuned the interaction must be. An atom responds most strongly to light near a particular resonant frequency. Resonance is familiar from ordinary objects. Push a child on a swing at the right timing and the motion grows. Push at the wrong timing and much of the effort is wasted. An atom does not swing back and forth in the same way, but the term captures the idea that the response becomes strong at a particular frequency. Laser light can be made narrow enough in frequency to take advantage of this. Ordinary white light contains a wide range of frequencies. A lamp shines many colours at once, even when our eyes combine them into something that appears white. A laser can concentrate its light into a much narrower range. That precision allows physicists to choose whether the atom absorbs strongly, weakly, or almost not at all. The width of the atomic response is not infinitely narrow. The excited state lasts for only a limited time, and that gives the transition a natural range of frequencies over which absorption can occur. Laser intensity also affects the response. At high intensity, the atom cannot absorb without limit, because it must spend time in the excited state before it can return and absorb again. There is therefore a maximum average rate at which the atom can scatter photons on a given transition. Increasing the laser power beyond a certain point does not make the atom respond proportionally faster. It is a little like trying to ring a doorbell again while the person inside is still walking toward the door. More pressing does not create more people. The maximum scattering rate sets a limit on the force that the beam can apply. For atomic physics, this force can be substantial. For a person, it would be hopelessly small. If a laboratory laser were aimed at a bowling ball, the ball would not roll away in alarm. An atom, however, has so little mass that the same momentum transfer can change its speed noticeably. This difference in scale is one reason atomic physics often surprises us. We are used to judging forces by what they do to chairs, doors, cups, and other objects that contain enormous numbers of atoms. A force too weak to move a grain of dust can still be powerful when directed at one atom. Radiation pressure was discussed long before laser cooling became practical. Scientists understood that light could carry momentum, and experiments confirmed that light could exert force. The development of lasers changed what could be done with that fact. A laser provided direction, intensity, frequency control, and coherence. It turned a general physical effect into a precise tool. Early experiments used light to deflect atomic beams. Researchers could observe atoms changing direction after interacting with resonant light. This was already remarkable. An invisible stream of atoms could be steered by another invisible stream, with detectors revealing the result. From steering, it was natural to ask whether the same force could slow atoms, hold them, or cool their random motion. Slowing a beam of atoms presents a practical difficulty. As the atoms lose speed, the frequency they experience changes. A laser that was resonant when the atoms were moving quickly may no longer be resonant after they slow down. The very success of the slowing process can make the laser stop working. One solution is to change the laser frequency as the atoms slow. Another is to use a magnetic field that changes along the path, shifting the atomic transition so the same laser remains effective. This arrangement is called a Zeeman slower. The name comes from the Zeeman effect, in which magnetic fields shift atomic energy levels. Inside such a device, atoms enter at high speed and move against a laser beam. The magnetic field is designed so that the changing atomic resonance compensates for the changing Doppler shift. The atoms continue absorbing light while they decelerate. By the time they leave, they may be slow enough to capture in another cooling system. The apparatus can be long because stopping takes distance. Even a strong optical force needs time to remove a large amount of momentum. The atom is not struck once and stopped. It is nudged again and again, with each photon taking away a little of its forward motion. There is a useful lesson here about what the light is actually doing. It is not acting like a wall. A wall stops an object through electric forces between atoms in the wall and atoms in the object. Laser light slows an atom through repeated absorption and emission. The atom remains in free space, and its path changes without touching a solid surface. This contactless control is one of the great advantages of light. Physical surfaces would disturb cold atoms. A collision with a warm wall would transfer energy and usually remove the atom from the experiment. Light can reach into a vacuum chamber and apply force without introducing material objects into the region where the atoms are held. Magnetic fields can also act without contact, but they depend on the magnetic properties of the atomic state. Light offers another level of selectivity. A beam can be aimed at one location, tuned to one transition, switched quickly, and shaped into patterns. With several beams and carefully chosen frequencies, researchers can create forces that depend on position, velocity, and internal state. The phrase optical force covers several related effects. Radiation pressure from absorption and spontaneous emission is the most direct. There are also forces caused by the way an atom's energy changes in a varying light field. These are often called dipole forces. They can pull atoms toward bright regions or push them toward dark regions, depending on how the light is tuned. Dipole forces are important for optical traps, where atoms can be held near the focus of a laser beam or inside patterns formed by interfering beams. Yet the basic cooling story begins with scattering force, because it provides a straightforward way to oppose motion. The atom absorbs a directed photon, emits in a random direction, and loses average momentum along the chosen axis. Random emission does introduce heating. Every spontaneous photon gives the atom a recoil in an unpredictable direction. Over many events, the average recoil may be zero, but the fluctuations are not. The atom performs a small random walk in momentum. One emission pushes it left, another right, another upward. This adds uncertainty to its motion. Cooling therefore involves a competition. Directed absorption removes motion in a controlled way, while random emission adds some motion back. At ordinary atomic speeds, the cooling effect can dominate strongly. At very low speeds, the random recoils become important and set a limit on how cold this simple process can make the atoms. That limit does not mean the method has failed. It means the process has reached a balance. The light continues scattering, but the average cooling is matched by recoil heating. More advanced techniques can change the balance and reach lower temperatures, but they still rely on careful control of light and atomic states. Another source of heating can come from laser noise. If the frequency or intensity fluctuates, the force on the atoms fluctuates. Misaligned beams can push the cloud away from the desired region. Background gas collisions can kick atoms out of the trap. Stray magnetic fields can shift the transitions. Cooling experiments are sensitive because the desired motion is so small that disturbances which seem minor on a human scale can become decisive. The vacuum chamber reduces collisions with surrounding gas. The lasers are locked to stable references. Optical components are mounted carefully. Magnetic fields are controlled with coils and shielding. None of these measures changes the basic idea, but all of them are needed to make the idea work consistently. It's also possible to observe the force directly through fluorescence. When the atom scatters photons, some emitted light reaches a detector. A bright cloud is usually scattering many photons. The brightness provides information about how many atoms are present and how strongly they are interacting with the lasers. Yet brightness alone does not reveal temperature. A cloud can scatter strongly while still moving too quickly for a particular experiment. Researchers measure temperature by releasing the atoms and watching how the cloud expands. A warmer cloud expands faster because its atoms have a wider spread of velocities. A colder cloud expands more slowly. This measurement returns us to the central meaning of cooling. The atoms are not cold because they look dim, because the chamber is refrigerated, or because the laser has a blue color on a screen. They are cold because their random velocities have become small. The push from light gives physicists a way to control those velocities. One beam can slow a directed atomic stream. Opposing beams can act on motion in both directions. Additional beams can extend the control to every spatial direction. But for the arrangement to cool rather than merely squeeze or push the cloud around, each moving atom must preferentially absorb from the beam that opposes its motion. A stationary atom sits between two opposing beams and receives nearly balanced pushes. An atom drifting to the right needs to absorb more photons from the beam travelling left. An atom drifting left needs the opposite. The lasers themselves do not watch the atoms and adjust individually. The selection happens automatically because motion changes the frequency each atom experiences. That frequency shift turns radiation pressure into a velocity-dependent force. It allows the light to distinguish, in effect, between an atom moving toward a beam and one moving away from it. Once that distinction is in place, two ordinary-looking beams can create resistance in empty space, and a fast atomic cloud can begin to behave as though it is moving through something thick. That thick resistance does not come from air, liquid, or any material surrounding the atoms. The vacuum remains almost empty. What changes is the way each moving atom sees the light approaching it, and this is where the Doppler effect becomes the quiet sorting mechanism behind laser cooling. Most people first meet the Doppler effect through sound. A vehicle approaches with its siren sounding at a steady pitch. As it comes closer, the pitch seems higher. After it passes and moves away, the pitch drops. The siren itself has not suddenly changed its mind about which note to play. The difference comes from motion between the source and the listener. As the vehicle approaches, each new sound wave is released from a position slightly closer to you than the previous one. The waves arrive more closely packed, and you hear a higher frequency. Once the vehicle is moving away, the waves reach you more spread out, and the frequency sounds lower. Light can also be shifted by relative motion. The details are not identical because light does not need air or another material through which to travel, but the central idea remains useful. When an atom moves toward a beam of light, the frequency it experiences is shifted upward. When it moves away from the beam, the experience frequency is shifted downward. The atom does not know that the laboratory laser has remained perfectly stable. From the atom's point of view, motion has changed the light. That change can be used to make the atom absorb from whichever beam is opposing its movement. The laser frequency is deliberately set a little below the frequency that a stationary atom would absorb most strongly. Physicists often describe this as tuning the light to the red side of the atomic transition. Red light has a lower frequency than blue light, so the phrase red detuned means that the laser frequency has been placed slightly below resonance. The beam does not necessarily look visibly red. The name describes its position relative to the transition, not always a colour that human eyes could identify. Many cooling lasers operate at wavelengths that appear red, near infrared, violet, or in ranges that people cannot see at all. Atomic language is not always considerate enough to match the labels on a box of crayons. Consider an atom moving toward one of these red detuned laser beams. Because the atom approaches the light, the Doppler shift raises the frequency from the atom's perspective. Light that was slightly too low in frequency in the laboratory frame now appears closer to resonance. The atom becomes more likely to absorb a photon from that beam. The absorbed photon pushes against the atom's motion. An atom moving away from the same beam experiences the opposite shift. The light appears even lower in frequency and farther from resonance. Absorption becomes less likely. The beam therefore pushes most strongly on atoms moving toward it, which is exactly what is needed for slowing. Now place a second beam on the opposite side. The two beams travel toward one another and have the same red detuned frequency. An atom moving to the right approaches the beam coming from the right. That beam appears shifted closer to resonance and pushes the atom left. The atom is moving away from the beam coming from the left, so that beam appears farther from resonance and has less effect. If the atom moves left, the roles reverse. It approaches the beam coming from the left, absorbs more photons from it, and receives pushes toward the right. Whichever way the atom moves, it's more likely to absorb light from the beam travelling against it. The process does not need a camera to track the atom. No computer has to calculate its direction and switch the lasers at precisely the right instant. The Doppler shift makes the selection automatically. This is the trick that turns two opposing beams into a cooling system. The stationary atom sitting near the centre sees both beams at roughly the same frequency. Since both are tuned below resonance, it absorbs less strongly than a moving atom that approaches one of them. When it does absorb, the average pushes from the two sides are balanced. There is no strong reason for it to accelerate in either direction. A moving atom is treated differently because its motion brings one beam closer to resonance and moves the other farther away. The faster it travels within a useful range, the larger the difference becomes. That means faster atoms experience a stronger force opposing their movement. Slower atoms experience a weaker force. The light behaves somewhat like friction. Ordinary friction opposes motion when two surfaces rub together. Air resistance grows as an object moves through air. Here, the atom is travelling through a vacuum, yet its velocity determines how strongly the lasers push back. The comparison has limits. Normal friction converts organised motion into random motion and heat. Doppler cooling uses light to remove random atomic motion and carry energy away in scattered photons. Still, from the perspective of an atom trying to cross the region, the beams create a resistance that increases with motion. Imagine walking through a corridor with people on both sides gently tossing soft balls toward you. When you stand still, the throws are balanced. When you move toward one side, the people ahead somehow become much better at hitting you, while those behind become less interested. Every time you take a step, more balls arrive from the direction you're heading and push you back. Walking becomes difficult, even though nothing solid blocks the corridor. Atoms do not experience inconvenience, embarrassment, or the suspicion that the corridor was designed by a particularly unhelpful committee. They simply scatter photons, but the result is similar. Motion causes opposition. The choice of laser frequency is crucial. Suppose the lasers were tuned exactly to the frequency preferred by stationary atoms. A stationary atom would scatter many photons from both beams. That would create strong random recoil from spontaneous emission, adding unnecessary motion. Meanwhile, atoms moving quickly might see both beams shifted away from resonance and scatter less effectively. Setting the frequency slightly below resonance changes the situation. Stationary atoms interact less. Moving atoms that approach a beam shift it into better alignment with the transition. The system favours the atoms that need slowing. If the laser frequency is placed too far below resonance, however, even moving atoms may not shift it close enough to be absorbed. The beams then pass through the cloud with little effect. If the frequency is too close to resonance, the atoms scatter strongly even when nearly stationary, increasing recoil heating and reducing the useful velocity dependence. Researchers must choose the detuning, intensity, and beam size to match the atoms they want to cool. A cloud arriving with a large spread of speeds may require broad, intense beams or several stages. Atoms already moving slowly can be cooled with gentler settings. There is a range of velocities over which Doppler cooling works effectively. Atoms moving too fast may see the opposing beam shifted beyond the transition rather than toward it, depending on the laser frequency and atomic structure. Others may cross the cooling region before scattering enough photons to slow significantly. This is why atoms are often slowed before entering the main cooling region. A device such as a Siemens slower can reduce the speed of an atomic beam. Once the atoms are within the capture range, opposing laser beams can cool them more effectively. The word capture can be slightly misleading. Doppler cooling by itself reduces velocity, but it does not necessarily return atoms to one location. If an atom is far from the center and moving slowly, balanced beams may not push it back. It can still drift away. Cooling controls velocity. Trapping controls position. The two are often combined, but they are not the same operation. A traffic officer can slow cars without directing them into a parking space. In a similar way, opposing red detuned beams can reduce atomic motion without creating a restoring force toward the center. Before adding a trap, it helps to see how the cooling extends beyond one direction. Two beams can cool motion along a single line. Real atoms move through three-dimensional space, so laboratories commonly use three pairs of opposing beams. One pair acts from left and right, another acts from front and back, a third acts from above and below. The beams overlap in the same region. An atom moving in any direction has some component of motion along one or more of these beam axes. The relevant beams oppose those components. After many scattering events, motion is reduced throughout the cloud. Perfect alignment matters. If one beam is stronger than its opposite, the cloud receives a net push. If the beams do not overlap correctly, atoms may be driven out of the cooling region. If their polarizations are wrong, the internal atomic states may respond in unwanted ways. The laboratory arrangement can look like a small intersection built entirely from light. 6 beams enter the vacuum chamber, all meeting where the atoms are expected to gather. Mirrors and lenses shape them. Optical fibers may deliver light from laser systems located elsewhere on the table. Detectors watch the resulting glow. Inside the crossing beams, atoms scatter photons rapidly. To the atoms, each direction of motion brings one beam closer to resonance. Their random movement is damped. A cloud that entered as a fast stream can become a much slower collection. This arrangement is often called optical molasses. The name is descriptive rather than literal. There is no sticky substance in the chamber. The atoms do not become coated, and cleaning the apparatus does not require warm water and a regrettable amount of patience. They simply experience a velocity-dependent force that resembles the resistance of a thick fluid. Optical molasses can reduce atomic temperatures to extremely low values. The exact result depends on the element and the details of the transition. At such temperatures, the average motion becomes slow enough that atoms can remain in a small region for much longer than they would at room temperature. Still, the cooling cannot continue without limit. Each absorption provides a directed push, but each spontaneous emission produces a random recoil. As the atoms become slower, the helpful Doppler force becomes weaker. Near rest, an atom sees the 2 opposing beams at almost the same frequency and absorbs from both at nearly equal rates. Random emission continues to disturb its motion. At some point, the cooling from the velocity-dependent force balances the heating from recoil. The cloud reaches a minimum temperature associated with this simple Doppler process. This is known as the Doppler cooling limit. No numerical value is needed to understand the reason for it. Cooling relies on scattering photons, and scattering photons includes random recoil. The same cycle that removes motion also introduces fluctuations. Once the remaining motion becomes small enough, those fluctuations prevent further improvement. The limit is not universal in the sense of being identical for every atom. It depends on the lifetime and natural width of the atomic transition. Some transitions allow lower Doppler temperatures than others. Narrow transitions can provide more selective cooling, though they may produce weaker forces and capture smaller ranges of velocity. Atomic physicists therefore choose transitions with particular jobs in mind. A broad transition can be useful for catching and slowing fast atoms. A narrower transition can then cool them further. Several cooling stages may be used, each taking over where the previous one becomes less effective. There is another subtle point hidden inside the frequency shift. From the laboratory perspective, the atom absorbs a photon from light tuned below resonance. Yet the atom still needs the correct energy to make its internal transition. Its motion supply is part of the difference. When the atom approaches the beam, the interaction draws a small amount of energy from its kinetic motion. Later, when the atom emits a photon, the outgoing light carries away the internal transition energy, along with that extracted amount, averaged over the process. The atom ends with less kinetic energy than it had before. The reduction from one event is tiny. Repeated scattering steadily drains motion from the cloud. This explains why the scattered light can carry away more energy than the laser light originally delivered to the atom. The extra energy is not mysterious. It came from the atom's movement. The laser acts as a carefully arranged route through which kinetic energy leaves as light. A household refrigerator also moves energy rather than destroying it. Heat is removed from the interior and released elsewhere, which is why the back of a refrigerator can feel warm. Laser cooling is very different in its machinery. but the same general rule applies. Cooling one system means energy must go somewhere else. Here, that somewhere is the light scattered out of the atomic cloud. The emitted photons leave in many directions. Some strike the chamber walls, some reach cameras and detectors, most simply disappear into the surrounding apparatus. Together they carry away energy that once belonged to atomic motion. The laser itself supplies energy to drive the repeated transitions, so the complete laboratory system is not becoming colder without cost. Electricity powers the lasers, electronics stabilize them. Cooling water or fans may remove heat from the equipment. A room containing a laser cooling experiment is not likely to become chilly because the atoms are generously refrigerating the building. Only the selected cloud reaches the very low temperature. The surrounding apparatus remains much warmer. This contrast can be enormous. The chamber walls may be near room temperature, while the atoms inside are among the coldest objects in the universe. They avoid rapidly warming because the vacuum greatly reduces contact with the walls and surrounding gas. The atoms interact mostly with the controlled laser beams and magnetic fields. A stray collision with an ordinary gas molecule can transfer enough energy to knock a cold atom out of the experiment. For this reason, the chamber pressure must be extremely low. Pumps remove air, and the materials inside are chosen and cleaned to reduce the release of trapped gases. Even after the chamber is prepared, background collisions slowly remove atoms. A cold cloud does not remain forever. Researchers may continuously load new atoms or perform experiments during the limited interval before too many are lost. The Doppler mechanism itself is dependable, but real atoms add complications. Many atoms have several magnetic sublevels within the energy states used for cooling. The probability of absorbing light depends on the polarization of the beam and the atom's internal state. After scattering several photons, an atom can be redistributed among these sublevels. It may become less responsive to one beam and more responsive to another. In some cases, this internal structure improves cooling beyond the simple Doppler picture. In others, it creates dark states that stop interacting with the light. Physicists control polarization to manage these effects. Circularly polarized light can favor particular transitions. Magnetic fields can shift the sublevels. Additional beams can return atoms from unwanted states. The basic explanation remains intact, but the actual experiment becomes a carefully coordinated system. Frequency selects velocity. Polarization selects internal transitions. Intensity controls the scattering rate. Beam direction determines the push. Magnetic fields influence where and how strongly the atom responds. This level of control is one reason laser cooling became so important. It does more than lower temperature. It prepares atoms in known conditions. Their motion, position, and internal state can all be adjusted with light. Such preparation allows precise tests. When atoms are moving slowly, researchers can examine their spectra without large Doppler broadening. In a warm gas, atoms move toward and away from a laser at many speeds. Each one sees a slightly different frequency, so the measured spectral line becomes spread out. Cooling narrows that distribution. The atoms experience more nearly the same frequency. Fine details that were hidden inside a broad blur can appear. The Doppler effect, which first creates the problem of broadened atomic lines, also provides the solution for cooling them. Motion shifts the frequencies seen by the atoms, making measurements less precise. Carefully detuned lasers use those same shifts to remove the motion. Nature has a certain efficiency in reusing its inconveniences. The same method also demonstrates that cooling does not require measuring each atom individually. Nobody records the speed of every particle and sends it a custom photon. The physical arrangement responds to velocity automatically. Fast motion creates a larger shift. The shift changes absorption. Absorption changes force. The force reduces the motion that caused the shift. It is a feedback process built directly into the interaction. As the atom slows, the Doppler shift becomes smaller. The opposing beam moves farther from resonance again, and the slowing force weakens. This prevents the beam from applying the same strong push after the atom has nearly stopped. the system naturally becomes gentler as the target velocity approaches zero. Not every atom stops at precisely zero velocity. Random recoil keeps the cloud moving, and each atom follows a changing path. Temperature describes the statistical spread of those motions. Cooling makes the spread narrower, but the cloud remains active on the microscopic scale. Seen through a camera, the atoms may form a small glowing region. Their movement is too small and fast to follow individually. The glow appears steady, even though millions of absorption and emission events are taking place. The calm appearance is produced by constant activity. Once the beams are switched off, the resistance disappears immediately. The atoms continue moving with whatever velocities they have at that moment. The cloud expands. Measuring that expansion reveals how cold it was. If the light remains on but there is no position-dependent trapping force, atoms can still wander out of the beam intersection. Optical molasses slows them, but does not securely hold them in place. Gravity can also pull them downward, though the light forces are often strong enough to influence their motion for a while. To keep the cloud gathered near the centre, the system needs a way to notice not only how fast an atom is moving, but also where it has gone. An atom that drifts left should feel a push right even if it is moving slowly. An atom that drifts upward should be encouraged downward. Velocity-dependent cooling must be joined by a position-dependent restoring force. Light alone, arranged as simple opposing beams, does not provide that correction. Magnetic fields can change the atomic resonance across space, allowing the lasers to respond differently on opposite sides of the chamber. With the right field pattern and beam polarizations, the same scattering process that slows the atoms can also guide them back toward the center. The result is one of the most widely used tools in experimental atomic physics. It combines the Doppler trick with a magnetic field, turning optical molasses from a region of resistance into a place where cold atoms can be caught and held. The result is one of the most widely used tools in experimental atomic physics, but before the magnetic field is added, it is worth spending some time inside the quieter arrangement that comes first. 6 laser beams cross in a vacuum chamber, 2 along each direction of space, and together they create optical molasses. The name suggests something sticky and slow, which is exactly the intended image. An atom moving through the crossing beams feels resistance from whichever beam it approaches. The faster it moves, the stronger the opposing push becomes within the useful range of the system. There is no liquid in the chamber, no surface dragging against the atom, and almost no ordinary gas. The resistance comes entirely from repeated exchanges of momentum with light. Picture an atom entering the illuminated region from the left. It is moving to the right, so it approaches the laser beam coming from the right side. Because of the Doppler shift, that beam appears closer to the frequency the atom absorbs most strongly. The atom takes in a photon and receives a push toward the left. It then releases a photon in a random direction. A moment later, it absorbs again. The process repeats until its motion to the right has been reduced. If the atom changes direction and begins moving left, the other beam becomes more effective. It now approaches the beam coming from the left side, so that beam provides the stronger opposing push. The light does not commit to one direction. It responds to the atom's motion through the frequency shift created by that motion. The same thing happens along the other 2 directions. An atom rising through the chamber encounters stronger resistance from the downward travelling beam. An atom falling encounters stronger resistance from the upward travelling beam. Motion toward the front is opposed from the front, and motion toward the back is opposed from the back. Every direction is covered by some combination of the 6 beams. An atom rarely travels neatly along one beam axis. It may move upward, sideways, and forward at the same time. Its motion can be considered as a combination of movement along the 3 beam directions. Each pair of lasers reduces the part of the motion aligned with it. Together, the beams slow the full motion of the atom. This is why optical molasses can cool a cloud rather than merely push it. A single beam produces a net force in one direction. 3 balanced pairs produce forces that depend on velocity and oppose it from all sides. The average position of the cloud may remain near the beam intersection for a while, but the important change is happening in the distribution of speeds. At the beginning, atoms in the cloud have a wide range of velocities. Some are relatively slow, others are fast. They travel in different directions and cross the illuminated region at different rates. The faster atoms generally experience stronger Doppler shifts, so they scatter more photons from the beams opposing their motion. They lose speed more quickly. As the cloud cools, its velocity distribution becomes narrower. The atoms do not all acquire exactly the same speed, and they do not become perfectly motionless. Instead, extreme motions become less common. The cloud changes from a restless crowd rushing in every direction into a much calmer gathering, whose members still move but no longer seem determined to leave immediately. The slowing can happen remarkably quickly. Atomic masses are tiny, and photons can be scattered millions of times per second. Even though each push is small, the repeated sequence can reduce speed in a short interval. An atom that would normally cross the chamber almost instantly can be slowed enough to remain within the laser beams for much longer. This extra time is valuable. Fast atoms give researchers only a brief opportunity to observe them. Slow atoms can be measured, manipulated, transferred into traps, or used in precision experiments. Laser cooling does not simply change a number called temperature. It changes how long the atoms remain available, and how carefully their behavior can be studied. The word molasses also helps describe another feature of the force. In a thick fluid, resistance depends on motion. Stop moving, and the resistance disappears. Optical molasses behave similarly near the center of its useful range. A stationary atom receives nearly balanced pushes from all directions. Since it is not moving toward one beam more than another, no beam is strongly favored by the Doppler effect. Once the atom begins drifting, a difference appears. The beam ahead becomes more resonant from the atom's point of view, and the beam behind becomes less resonant. The imbalance pushes against the drift. The system dampens motion without needing to know why the atom started moving. This damping is useful, but it should not be confused with confinement. A bowl holds a marble because moving away from the bottom raises the marble and creates a force back toward the center. Optical molasses does not provide that kind of position-based return. It acts mainly when the atom is moving. Suppose an atom has drifted several millimeters away from the center and then becomes nearly stationary. If the opposing beams are still balanced at that location, the atom may feel almost no net force. Nothing tells it that the middle of the apparatus is the preferred address. A small disturbance can send it farther away, and gravity can gradually pull it downward. This is why optical molasses is a cooling region rather than a complete trap. It can make atoms slow, but it cannot reliably hold them in one place for long periods. The distinction is easy to miss because a cold cloud may appear suspended for a short time. The atoms are moving so slowly that they do not spread quickly, which can look like confinement. Eventually, however, the cloud expands and falls. The experiment is also sensitive to the balance between the beams. If the beam from the left is slightly stronger than the beam from the right, the cloud experiences a gentle push toward the right. If the upper beam is weaker than the lower one, the atoms may drift upward. Small differences in intensity can produce noticeable motion because the atoms are so light. Researchers therefore adjust the beams carefully. They try to match the intensity of each opposing pair, align the paths so they overlap, and choose beam sizes large enough to cover the desired region. Mirrors are adjusted by tiny amounts. Photodetectors compare powers. Optical fibers help deliver stable beams, though they can introduce their own alignment problems. A laboratory table used for laser cooling often appears crowded because each simple-looking beam requires several supporting components. Lenses expand or focus the light. Wave plates control polarization. Mirrors direct the path. Devices shift the frequency. Shutters turn beams on and off. Photodiodes monitor power. Locking electronics keep the laser from wandering away from the atomic transition. The atoms see only the final beams entering the chamber. The researchers see the entire network required to make those beams behave. Frequency stability is especially important. The cooling depends on the laser remaining slightly below resonance. If the frequency drifts too close, stationary atoms scatter too much and recoil, heating increases. If it drifts too far away, the atoms stop interacting effectively. The useful range can be narrow, so the laser is usually compared with a stable atomic reference and corrected continuously. Intensity must also be chosen with care. Stronger light can increase the scattering rate and make the damping force larger, which helps capture faster atoms. Too much intensity broadens the atomic response and increases random scattering. It can also make the simple relation between velocity and force less clean. The best setting depends on the stage of the experiment. At first, relatively strong beams may be used to slow a warm or fast sample. Later, the intensity can be reduced and the frequency moved farther below resonance to reach a lower temperature. The cooling sequence may change over a few thousandths of a second, with computer-controlled devices adjusting the light much faster than a person could turn a knob. The atoms themselves respond even faster. Their excited states last for only a tiny fraction of a second. Absorption and emission occur again and again, while the control system changes the overall conditions more gradually. The scattered light gives the cloud its visible glow. Cameras placed outside the chamber collect a small portion of the fluorescence. The image can reveal the location, shape, and approximate number of atoms. A brighter cloud usually contains more atoms or scatters more strongly, though those possibilities must be separated carefully. The image may look like a soft ball of light. It is tempting to think of it as a tiny lamp placed in the chamber, but the glow is made from individual atoms releasing photons after excitation. Each point of light comes from an event too small and fast to see alone. The camera gathers many events into a smooth picture. To measure temperature, the cooling beams are switched off. Without the optical resistance, the atoms travel freely. The cloud begins to expand because different atoms have different velocities. A camera records its size after one or more delays. A warmer cloud expands rapidly. A colder cloud expands slowly. By comparing the size at different times, researchers estimate the spread of atomic velocities and therefore the temperature. This method is called time-of-flight measurement because it observes how far the atoms move during a known period of free flight. The method sounds straightforward, but the details require care. The imaging light can push the atoms. The camera has limited resolution. The initial cloud size must be known. Gravity moves the entire cloud downward while it expands. If the atoms interact strongly with one another, those interactions can alter the expansion. Even so, time-of-flight imaging is one of the standard ways to tell whether the molasses has worked. It converts invisible microscopic motion into a visible change in cloud size. Another method uses the way atoms absorb a probe beam. A weak beam passes through the cloud and a camera records the shadow. The depth and shape of the shadow reveal how many atoms were present and where they were located. Repeating the measurement after different expansion times provides the temperature. The probe usually destroys or disturbs the sample, so each image may require a fresh cloud. The experiment is repeated many times under nearly identical conditions. Atomic physics often advances through patient repetition, followed by careful arguments about why one run was slightly different from the others. The lowest temperature predicted by the basic Doppler model comes from a balance between damping and random recoil. Directed absorption reduces motion. Spontaneous emission adds unpredictable kicks. As the atoms slow, the Doppler difference between opposing beams becomes smaller. Cooling weakens while recoil remains. At the balance point, the average temperature stops falling. This Doppler limit was once expected to describe the final temperature of optical molasses for many common atoms. Experiments then produced a surprise. Some atoms became colder than the simple limit predicted. The reason was hidden in details that the simplest picture had ignored. Real atoms can have several internal magnetic states, and the laser beams have polarization. When light with different polarizations overlaps, It creates a changing pattern of how strongly each internal state interacts with the light. An atom moving through that pattern can repeatedly climb small energy hills and be shifted into a lower energy state near the top. The process removes additional kinetic energy. It is often described through the story of Sisyphus, the figure from Greek mythology who continually pushed a stone uphill only to have it roll down again. In this cooling process, the atom repeatedly climbs an optical energy hill. Before it can regain the energy by moving down the other side, light changes its internal state and places it near the bottom of another hill. The atom must climb again, losing more motion each time. This effect is called Sisyphus cooling. It is one of several forms of cooling that operate below the ordinary Doppler limit. It depends on polarization patterns and internal atomic structure, rather than only on the frequency shift from motion. The name makes the atom sound unfortunate, but the atom has no awareness of the repeated climb. It follows the available transitions. The researchers benefit from the result and generally avoid apologizing to the sample. Sisyphus cooling explains why optical molasses can perform better than a simple two-state atomic model suggests. The atom is not merely a particle absorbing from one of two beams. It has multiple internal states, and those states respond differently across the light field. Motion through the field changes both external and internal energy. This deeper mechanism does not replace Doppler cooling. The Doppler force is still important, especially for atoms moving faster. As the sample becomes slower, polarization-based effects can take over and reduce the temperature further. The cooling process changes character as the velocity decreases. Not every element offers a convenient set of transitions for these methods. Alkali metals such as sodium, rubidium, and cesium became common choices because their atomic structures and accessible laser wavelengths make cooling practical. Other atoms require different laser systems, additional repumping frequencies, or narrow transitions. Molecules are more difficult because they have rotational and vibrational states in addition to electronic states. After absorbing and emitting light, a molecule can fall into many possible internal states and stop participating in the cooling cycle. Researchers have nevertheless developed laser cooling for selected molecules by choosing favourable structures and adding several repumping lasers. The complexity rises quickly. An atom may require one main cooling frequency and one repumping frequency. A molecule may require a collection of frequencies to prevent population from leaking into dark states. The light has to keep gathering the particles back into the cycle. Optical molasses also has a limited capture velocity. An atom moving too quickly may see the laser shifted too far from resonance. It crosses the beam intersection before scattering enough photons to slow down. The molasses cannot catch every atom entering the chamber. This is why experiments often begin with a source that produces a directed atomic beam, followed by a slowing stage. The atoms may emerge from a heated oven, where many are moving rapidly. A carefully arranged counter-propagating laser and magnetic field reduce their forward speed. Only then do they enter the region of crossed beams. The cooling region accepts atoms within a certain range of speeds and positions. Those outside the range are lost to the chamber walls. Efficiency matters because the number of useful atoms determines the strength of later measurements. Even when the optical molasses works well, the cloud has a limited lifetime. Background gas collisions remove atoms. Imbalances in the beams cause drift. Gravity pulls the sample downward. Random scattering slowly spreads it. If the lasers are turned off, expansion begins immediately. For many experiments, a brief period of molasses is enough. The atoms can be cooled and then transferred into an optical or magnetic trap. In other cases, researchers want a system that loads continuously and holds the atoms at the centre while cooling them. That requires a force that depends on position as well as velocity. The beams already know how to oppose motion because the Doppler shift changes the frequency an atom experiences. To create confinement, the atomic resonance must also change with location. Then, an atom wandering away from the centre can be made to absorb more strongly from the beam that pushes it back. A magnetic field provides that spatial variation. It shifts the energy levels of the atom by different amounts at different positions. Combined with carefully chosen laser polarizations, the field turns the crossing beams into more than optical molasses. The light still slows the atoms, but it also begins to guide them toward the middle. The light still slows the atoms, but it also begins to guide them toward the middle. This happens when a magnetic field is arranged so that its strength changes across the cooling region. At the exact center, the field is close to zero. Move away in any direction, and the field becomes stronger. That change affects the internal energy levels of the atoms. The preferred absorption frequency is no longer exactly the same everywhere in the chamber. An atom on one side responds more strongly to one laser beam, while an atom on the opposite side responds more strongly to the beam travelling the other way. With the correct laser polarizations, an atom that wanders away from the center absorbs more photons from the beam, pushing it back. The farther it moves within the useful region, the larger the imbalance becomes. At the same time, the Doppler effect continues to oppose its velocity. The result is a magneto-optical trap. It cools because moving atoms are pushed against their motion. It traps because displaced atoms are pushed toward the center. Velocity and position are controlled at once. This is one of the most common starting points in experiments with cold atoms. A magneto-optical trap can collect atoms from a slowed atomic beam or from a thin background vapor. It can cool them, gather them into a small cloud, and hold them long enough for the next stage of the experiment. The apparatus usually combines 6 laser beams with a pair of magnetic coils. The beams are arranged in the same 3 opposing pairs used for optical molasses. The coils carry currents in opposite directions, producing a magnetic field that is zero near the center and grows stronger away from it. The field shape is sometimes called a magnetic quadrupole field. The name describes its spatial pattern, but the main point is simple. There is a central location where the magnetic influence is smallest, surrounded by regions where it increases. Consider an atom that drifts to the right. The magnetic field shifts its energy level so that it becomes more likely to absorb light from the beam travelling to the left. That beam gives it a push back toward the center. An atom drifting to the left experiences the opposite shift and absorbs more from the beam travelling right. The same correction occurs above, below, in front and behind. The lasers and magnetic field work together to give the cloud a preferred location. Polarization is essential to this process. Light has an electric field that oscillates as it travels, and the direction of that oscillation can be controlled. In circularly polarized light, the direction rotates as the beam moves forward. There are 2 possible senses of rotation. Atoms with magnetic sublevels respond differently to these 2 polarizations. The magnetic field shifts those sublevels differently depending on position. By choosing the polarization of each beam carefully, physicists make the inward pushing beam more effective than the outward pushing beam. The atom does not respond simply because one beam is brighter. It responds because the combination of local magnetic field, internal state, laser frequency, and polarization makes one transition more likely. If the polarizations are reversed, the trap may stop restoring atoms to the center. It may push them outward instead, which is not generally the desired result. A trap that expels its contents is less of a trap, and more of a very expensive suggestion to leave. Alignment is therefore important. The beam directions, magnetic field, polarization, and frequency must agree with one another. A mistake in one part can reduce the number of trapped atoms or prevent the cloud from forming. When everything is adjusted correctly, the atoms gather near the center and emit light as they scatter photons. Through a camera, the cloud appears as a small glowing spot. Its size may range from a fraction of a millimeter to several millimeters, depending on the number of atoms and the conditions. The glow can be bright enough to see with a sensitive camera, and sometimes even with the eye under suitable conditions. What looks like a quiet floating light is a collection of atoms undergoing millions of absorption and emission events. The cloud is constantly being cooled and disturbed. The laser force slows the atoms. Random photon recoil adds motion. The magnetic field pushes displaced atoms inward. Collisions and imbalances push some of them out. The visible cloud is a steady state created by all these competing processes. Atoms can enter the trap while others leave it. When loading from a background vapor, warm atoms move through the chamber in every direction. Most pass through too quickly to be captured. A small fraction happen to enter the laser region, with velocities low enough for the beams to slow them. If they lose enough speed before escaping, the restoring force keeps them near the center. Over time, the trapped number grows. Eventually, the loading rate is balanced by losses from background collisions and other effects. The number of atoms can range from a few to many millions. The exact number depends on the element, vapor pressure, beam diameter, laser power, magnetic field, and vacuum quality. A larger beam can capture atoms over a wider region. Greater laser power can increase the slowing force. A better vacuum allows atoms to remain trapped longer. Increasing the atomic vapor supplies more candidates for capture, but too much vapor also causes more collisions. The experiment becomes an exercise in compromise. More atoms are useful, but the methods used to obtain them can shorten the trap lifetime or raise the temperature. The trapping force is gentle by everyday standards. It could not hold a grain of sand. For an atom, it is enough. The atom has so little mass that repeated photon pushes can reverse its motion and return it toward the center. Gravity still acts on the atoms. In many magneto-optical traps, the optical force easily balances gravity. The cloud may sit slightly below the exact magnetic center, because the upward and downward forces reach balance there. For atoms cooled on very narrow transitions, the light force can be weaker, and gravity becomes more noticeable. The cloud may sag or develop an unusual shape. Researchers account for this when transferring atoms into later traps. The term magnetic trap can also refer to a different system that uses magnetic fields without continuously scattering laser light. This distinction matters because a magneto-optical trap is excellent for collecting and cooling atoms, but it is not always the best place for the coldest or most precise measurements. The constant scattering of photons creates problems. Random recoil limits the temperature. Light shifts the atomic energy levels. Excited atoms can collide and escape. The fluorescence that makes the cloud visible also means the atoms are being disturbed. Once enough atoms have been collected and cooled, the lasers can be turned off, and the sample transferred into a trap based mainly on magnetic forces. Atoms can behave like tiny magnets because of their internal angular momentum and magnetic properties. In a non-uniform magnetic field, some atomic states are attracted toward regions of weaker field, while others are attracted toward stronger field. Static magnetic fields can create a stable minimum of field strength in free space. They cannot create a stable maximum in the same way. For that reason, magnetic traps usually hold atoms in states that seek low magnetic fields. These are often called low field-seeking states. The atoms experience an energy increase as they move into stronger field, so they are pushed back toward the minimum. A useful picture is a ball resting in a bowl. The lowest point represents the magnetic field minimum. Moving away raises the energy, so the atom tends to return. Unlike the ball, the atom does not roll on a surface. The bowl is an energy landscape created by magnetic fields. Only certain internal states can be trapped. If an atom is in a high field-seeking state, it moves toward a stronger field and may escape. Before loading the magnetic trap, researchers use light or radio frequency techniques to prepare the atoms in the appropriate state. This preparation is known as optical pumping when light is used. The atoms scatter selected photons until most of them accumulate in the desired magnetic sublevel. The process is another example of using atomic selection rules rather than directly handling individual particles. The magnetic trap can be formed with coils carrying carefully controlled currents. Different coil arrangements produce different field shapes. Some traps use a simple quadrupole field, similar to the one in the magneto-optical trap. Others add a bias field so that the minimum is not exactly zero. Avoiding a zero field can be important. Near a point where the magnetic field vanishes, the direction of the field changes rapidly. An atom moving through this region may fail to keep its internal magnetic orientation aligned. It can switch into an untrapped state and leave. These losses are sometimes called Majorana losses. The name comes from the physics describing transitions near the field zero, not from any tendency of the atoms to behave dramatically. More elaborate magnetic traps maintain a non-zero minimum. One widely used arrangement combines several coils to create confinement in all directions while protecting atoms from the zero field region. Magnetic traps have several advantages. They do not require constant resonant photon scattering. Once the atoms are loaded, the cooling light can be removed. The sample is then less disturbed by spontaneous emission and light-induced energy shifts. This makes magnetic traps useful for evaporative cooling. Evaporative cooling works by allowing the fastest atoms to escape, while the remaining atoms collide and redistribute their energy. It resembles the cooling of a hot drink as energetic molecules leave the surface, though the atomic version is controlled much more precisely. In a magnetic trap, the depth of the energy bowl can be gradually reduced. The most energetic atoms reach the edge and escape. The atoms left behind have a lower average energy. Removing fast atoms alone is not enough. The remaining atoms must collide with one another so that their energies are redistributed. After rethermalization, a new high-energy group forms. The trap depth is lowered again, and those atoms are removed. Repeated over time, the process can reduce the temperature far below what ordinary laser cooling can achieve. There is a cost. Each cooling step loses atoms. A successful sequence must remove energy faster than it removes useful density. If too many atoms are lost or collisions occur too slowly, the sample becomes small before reaching the desired temperature. The collision rate depends on density, speed, and the properties of the atomic species. Researchers adjust the trap shape to keep atoms close enough to collide. They also choose internal states that avoid unwanted losses. Some collisions help the gas rethermalize, others can eject atoms or change their internal states. At very high densities, 3 atoms may meet in a process that forms a molecule and releases enough energy to remove particles from the trap. Cold atom experiments therefore involve careful control of both temperature and density. A colder sample is not automatically better if almost no atoms remain. Magnetic trapping also has a limitation. It can hold only atoms with suitable magnetic states. The sample remains sensitive to variations in external magnetic fields. Nearby equipment, electric currents, and even metal components can alter the trapping potential. Coils generate heat and require stable power supplies. Current noise can shake the trap or change its depth. Large currents may need water cooling. The atoms may be extremely cold, while the apparatus responsible for holding them is doing its best impression of a radiator. For some experiments, optical traps provide a more flexible alternative. A focused laser beam can create an energy shift that attracts atoms toward the brightest part of the light. If the laser frequency is chosen well away from an atomic resonance, the atoms scatter relatively few photons. This kind of trap is called an optical dipole trap. It uses the interaction between the electric field of the light and the atom's induced response. The force is different from the repeated absorption force used in Doppler cooling. In a red detuned dipole trap, atoms are usually attracted toward regions of higher intensity. A tightly focused beam creates a small region where they can be held. 2 cross beams can provide stronger confinement in all directions. Because the light is far from resonance, spontaneous scattering can be low. The trap can hold different magnetic states and may work with atoms that are difficult to contain magnetically. Optical traps also allow researchers to apply magnetic fields more freely for other purposes. This becomes important when controlling atomic interactions or studying mixtures of internal states. The laser power must be stable. Any fluctuation changes the trap depth. The beam position must remain fixed. A small movement of a focused beam moves the entire trap and can heat the atoms. The optical components may be mounted on vibration-isolated tables, but nothing is perfectly still. Pumps vibrate. Cooling water flows. Air currents affect exposed beam paths. A door closing elsewhere in the laboratory can sometimes produce a visible disturbance in a sensitive signal. Researchers learn to identify these sources through repeated tests. A cloud that heats unexpectedly may be responding to laser noise, magnetic noise, poor vacuum, beam motion, or a timing problem. The atoms rarely provide a written complaint. In many experiments, atoms pass through several different environments. They begin in a hot oven or room temperature vapor. A laser slows them. A magneto-optical trap captures and cools them. Optical molasses reduces the temperature further. Optical pumping prepares an internal state. A magnetic or optical trap receives the sample. Evaporative cooling then brings it into a new temperature range. Each stage must hand the atoms to the next one efficiently. If the cloud is too large, too warm, or in the wrong state, the transfer fails. Timing matters because beams and fields must change in the correct order. The full sequence may last only seconds. During that time, lasers switch frequency, magnetic currents rise and fall, shutters open, detectors trigger, and the atoms move through several forms of confinement. The experiment is then repeated. A single data point may require many runs. A complete measurement may require thousands. Holding atoms is necessary because the most interesting low-temperature behavior does not appear while they are rushing through the chamber. The particles need time to collide, settle, and respond to controlled changes. A trapped sample can be probed with weak light. Its internal states can be changed with radio waves or microwaves. The trap can be tilted, compressed, split, or suddenly removed. Researchers watch how the cloud reacts and compare the result with predictions. At sufficiently low temperatures, the atoms stop behaving like a collection of independent tiny balls. Their quantum wave properties become important over larger distances. Identical particles may begin to occupy states collectively. Reaching that regime requires cooling beyond the basic Doppler limit. Laser cooling and magneto-optical trapping prepare the sample, but another stage must remove even more motion. Evaporative cooling is one route. Specialized laser methods provide another. These methods take advantage of internal states, dark states, narrow transitions, and carefully arranged light fields to reduce the random recoil that limited ordinary Doppler cooling. The atoms have already learned to slow down in optical molasses and gather near the center of a magneto-optical trap. The next challenge is to cool them when the usual scattering process has reached its balance, and when every random photon recoil begins to matter. The atoms have already learned to slow down in optical molasses and gather near the center of a magneto-optical trap. The next challenge is to cool them when the usual scattering process has reached its balance, and when every random photon recoil begins to matter. At first, Doppler cooling works very well. A moving atom sees one laser beam shifted closer to resonance, absorbs more photons from that direction, and receives a force opposing its motion. As the atom slows, the frequency difference between the opposing beams becomes smaller. The cooling force weakens. Spontaneous emission continues to give the atom random pushes, so a point is eventually reached where the useful slowing and the unwanted recoil balance one another. That balance creates the Doppler cooling limit. It is not the lowest temperature allowed by nature. It is only the lowest temperature expected from the simplest version of this particular cooling process. This distinction became important when experiments began producing atoms colder than the theory seemed to permit. The measurements were checked, the lasers were checked. The thermometers, which in these experiments are really observations of expanding atomic clouds, were checked. The atoms continued to be colder than expected. Nature had not broken the rules. The original model had simply left out some of the rules the atoms were following. The simplest explanation of Doppler cooling treats an atom as though it has one lower energy state and one higher energy state. It absorbs light, becomes excited, emits light, and returns to where it began. Real atoms usually have more internal structure. A single energy level may contain several closely related magnetic states, and each of those states can respond differently to the polarization of light. Polarization describes the orientation of the light's electric field. In a laser cooling experiment, different beams may carry different polarizations. When those beams overlap, they create a pattern that changes across space. An atom moving through the pattern does not experience the same interaction everywhere. Its internal energy rises and falls depending on its position and its magnetic state. The light creates a series of shallow energy hills and valleys. The atom begins to climb one of those hills using its kinetic energy. As it moves upward, it slows. Near the top, it absorbs light and is transferred into another internal state, whose energy landscape places it near the bottom of a different hill. The atom has lost the energy it used during the climb, but it does not get that energy back by rolling down the original side. It must climb again. This repeated climbing process is called Sisyphus cooling. The name refers to the figure from Greek mythology who was forced to push a stone uphill repeatedly. In the atomic version, the atom is the one doing the climbing, though it is given no stone and receives very little opportunity to discuss the arrangement. Each climb removes a small amount of kinetic energy. Light changes the atom's internal state before the lost motion can be recovered. After many cycles, the atom becomes much slower than ordinary Doppler cooling alone would predict. The process depends on the polarization pattern and the internal magnetic states of the atom. It works especially well for certain atomic structures, including several of the elements commonly used in cold atom laboratories. This type of cooling is often called sub-Doppler cooling, because it reaches temperatures below the Doppler limit. It does not reject the Doppler effect. Faster atoms are still first slowed by the velocity-dependent force. As their motion becomes smaller, the polarization-based mechanism becomes more important. The cooling method changes as the atoms slow. What begins as a frequency selection process becomes a repeated exchange between motion and internal state. There is still a limit. The atom continues to absorb and emit photons. Each emission adds recoil. Eventually, even the smaller motions produced by individual photons become important. The atom cannot be treated as though light provides perfectly smooth pressure. At this scale, every scattering event is noticeable. The recoil from one photon sets another natural temperature scale. Once the kinetic energy of the atom becomes comparable to the motion caused by a single photon, further cooling becomes more difficult. A method that depends on repeated random emission cannot easily ignore the disturbance created by those emissions. Physicists therefore look for ways to make atoms interact with light while reducing the number of spontaneous photons they release. One approach uses dark states. A dark state is an internal combination of atomic states that does not absorb the applied laser light. The atom becomes nearly invisible to the cooling beams, not because it has left the chamber, but because the different pathways for absorption interfere with one another. This can be useful when the dark state is connected to low motion. The cooling system is arranged so that faster atoms continue interacting with the light, while the slowest atoms are more likely to enter the dark state. Once there, they stop scattering and avoid additional recoil heating. The atoms that still move too quickly remain bright to the lasers. They absorb photons, lose motion, and may eventually join the dark population. The cooling resembles a waiting room in which the calmest visitors are quietly moved into a protected area, while the restless ones continue receiving attention. The comparison should not be taken too far, since real waiting rooms rarely use quantum interference, and would probably receive complaints if they did. A family of methods known as velocity-selective coherent population trapping uses this idea. Lasers connect several internal atomic states in a way that creates a dark state for atoms within a narrow range of velocities. Atoms outside that range continue scattering light. The selected velocity range can be centered close to zero. As the cooling proceeds, more atoms accumulate in states with very little motion. Because the coldest atoms scatter fewer photons, recoil no longer heats them as strongly. This allows temperatures below the ordinary recoil scale in certain directions. The process depends on coherence, meaning that the quantum phases of the internal states remain related in a controlled way. Coherence is delicate. Magnetic fields, collisions, laser noise, and other disturbances can destroy the relationship. The experiment must be stable, and the timing must be chosen carefully. Another method is Raman cooling. It uses pairs of laser beams to change an atom's internal state, while giving it a controlled momentum kick. The lasers are tuned so that atoms moving within selected velocity groups are transferred, while atoms already close to the desired velocity are left mostly untouched. After the transfer, optical pumping returns the atoms to their original internal state. This step includes spontaneous emission, but the overall sequence is designed so that more momentum is removed than added. The process is repeated with different settings. Each cycle targets another part of the velocity distribution. The cloud becomes narrower and colder. The word Raman comes from a type of interaction in which the atom changes between lower energy states through a process involving light, without remaining in the higher state for long. It is named after the physicist Chandrasekhara Venkata Raman, whose work on light scattering revealed how light can exchange energy with matter. Raman cooling offers precise control because the difference between two laser frequencies can be adjusted very accurately. The method can select velocities much more narrowly than a broad ordinary transition. This selectivity becomes valuable near the lowest temperatures, where the remaining motion is too small for conventional cooling forces to distinguish easily. Narrow atomic transitions provide another route. Some excited states last much longer than the states used for ordinary Doppler cooling. A longer lifetime corresponds to a much narrower frequency response. A narrow transition allows the laser to distinguish smaller Doppler shifts. That means it can remain sensitive to much slower atoms. The random photon recoil may also be smaller if the light has a longer wavelength, though the details depend on the element and transition. The disadvantage is that a narrow transition produces a weaker force. The atom cannot scatter photons as rapidly because the excited state lasts longer. Fast atoms may pass through the beam before the light slows them enough. For this reason, cooling often happens in stages. A broad transition first catches and slows the fast atoms. A narrow transition then takes over after the sample is already cold. Strontium and ytterbium are examples of atoms that offer useful narrow transitions. These elements are widely used in advanced atomic clocks. Their cooling sequences may begin with strong light that captures a large velocity range, followed by weaker light that reaches much lower temperatures. The second stage can produce clouds cold enough for precise spectroscopy and optical lattice clocks. An optical lattice is a repeating pattern of light that holds atoms at many separate locations. The atoms can be confined while their internal transitions are measured with extraordinary precision. Cooling is essential because motion would shift and blur the clock signal. The colder the atoms become, the less their movement interferes with the measurement. There are also techniques that use the shape of the trap itself. In sideband cooling, an atom is held tightly enough that its motion is restricted to distinct quantum energy levels. The cooling light is tuned to reduce the motion one level at a time. The atom changes its internal state while losing 1 unit of vibrational motion. Another light process returns the internal state without restoring the lost movement. Repeating the cycle moves the atom toward the lowest motional state of the trap. This method is common with trapped ions, and can also be used with neutral atoms in optical traps. It requires strong confinement and well-resolved motional levels. The laser frequency must distinguish the transition that removes motion from those that leave it unchanged, or add more. When sideband cooling succeeds, an atom can reach the ground state of its motion. This does not mean it becomes completely still. Quantum mechanics does not allow a confined particle to have exactly zero motion and a perfectly defined position at the same time. Even the lowest motional state contains a small, unavoidable amount of activity. That remaining motion is not ordinary heat in the familiar sense. It is part of the quantum structure of confinement. Laser cooling methods can bring atoms very far, but many experiments aiming for the coldest gases eventually use evaporative cooling. Once the atoms are trapped and dense enough to collide, the most energetic ones are deliberately removed. Imagine a container filled with balls moving at different speeds. Open a small exit positioned so that only the fastest balls can reach it. Those balls leave, and the average speed of those remaining becomes lower. In a trapped atomic gas, the exit is created by reducing the trap depth, or by changing the internal state of high-energy atoms so they are no longer confined. The fastest atoms escape. The rest collide and share their energy until the gas settles into a new distribution at a lower temperature. The trap is then lowered again. This process can continue through many stages. Each step sacrifices atoms to remove energy. The total number decreases, but the remaining sample becomes colder and more concentrated in the lowest energy states. A common magnetic trapping method uses radio frequency radiation. The magnetic field strength varies across the trap, so atoms at different positions have different internal transition frequencies. The most energetic atoms travel farthest from the center and reach regions of stronger field. Radio frequency energy is chosen to flip the internal state of atoms in those outer regions. Once flipped, they are no longer trapped and leave. Lower energy atoms near the center remain unaffected. As the sample cools, the radio frequency is adjusted so that the removal boundary moves inward. It is sometimes called an evaporation knife because it cuts away the high-energy part of the distribution. Nothing sharp enters the chamber, which is fortunate for both the atoms and the vacuum system. In an optical trap, evaporation can be achieved by gradually reducing the laser power. The energy bowl becomes shallower. The fastest atoms climb out, while slower atoms remain. Reducing the power also weakens confinement, causing the cloud to expand and lowering the collision rate. Researchers often change the trap geometry, or add other beams to keep the evaporation efficient. Collisions are essential because they allow the remaining atoms to rethermalize. Without collisions, removing the fastest atoms would leave holes in the velocity distribution, but it would not continuously produce a colder equilibrium gas. The collisions must occur often enough for the sample to redistribute energy, before too many atoms are lost through other processes. A good evaporation sequence can enter a favorable cycle. As the gas becomes colder and denser, useful collisions become more frequent, allowing cooling to proceed even faster. This is sometimes called runaway evaporation. The name sounds alarming, but it is generally welcomed in the laboratory. It means the cooling becomes increasingly efficient. Not all atomic gases cooperate. If the collision rate is too low, the sample does not rethermalize. If unwanted collisions are too strong, atoms are lost before reaching the desired temperature. The interaction strength depends on the element and internal state. It can also depend on magnetic field. In some atoms, researchers use a phenomenon called a Feshbach resonance to change the strength of collisions. By adjusting the magnetic field, they alter the energy relationship between colliding atoms and a molecular state. The effective interaction can become stronger, weaker, attractive, or repulsive. This control allows evaporation to be improved and opens the way to many later experiments. It also requires precise magnetic fields, because a small change can produce a large difference in the behavior of the gas. As the temperature falls, the wavelength associated with each atom's quantum motion grows. At ordinary temperatures, this wavelength is much smaller than the distance between atoms. Each particle can be treated approximately as a separate object following its own path. At lower temperatures, the wavelengths spread farther. Eventually, neighbouring atoms can no longer be described as completely separate. Their quantum waves overlap. This is the point toward which the entire cooling sequence has been moving. The hot source, the slowing laser, the magneto-optical trap, optical molasses, magnetic confinement, narrow line cooling, dark states, sideband cooling, and evaporation all remove forms of motion that normally hide collective quantum behavior. At first, cooling simply makes atoms easier to observe. Later, it changes the kind of object the gas becomes. The rules depend on whether the particles belong to one of two broad quantum families. Bosons can gather into the same quantum state. Fermions cannot all occupy an identical state, and instead fill available states in an ordered way. These differences are always present, but thermal motion usually overwhelms them. When the gas becomes cold enough, statistics begin to control visible properties. A gas of bosonic atoms may form a Bose-Einstein condensate. A large fraction of the atoms then occupies the same lowest energy state. The cloud behaves as a coherent matter wave, rather than a collection of independent particles. A gas of fermionic atoms forms a degenerate Fermi gas. The particles fill a range of quantum states even when the temperature is extremely low. Their behavior provides a controlled way to study physics related to electrons in solids, dense stars, and strongly interacting matter. These states are not produced by laser cooling alone. Laser cooling prepares the atoms so that evaporation and other methods can complete the journey. Without the early stages, too few atoms would be captured, and they would begin with far too much motion. The methods form a chain. Each one operates best within a particular range. Broad laser transitions catch fast atoms. Doppler forces reduce ordinary motion. Polarization effects cool below the first limit. Narrow transitions and dark states refine the sample. Traps hold the atoms while evaporation removes the energetic tail. No single beam performs the entire task. The lowest temperatures reached in laboratories are so far below everyday experience that familiar comparisons stop being useful. A household freezer, outer space, and the coldest natural environments are all warm compared with some prepared atomic gases, yet the surrounding laboratory may remain at room temperature. Researchers stand beside the apparatus, electronics release heat, pumps operate, and cables carry current. Inside a small region of the vacuum chamber, a cloud of atoms moves with almost no thermal energy. The cold is not created by cooling the whole room. It is created by isolating a small system and controlling which forms of energy are allowed to remain. As the motion decreases, the atom's wave nature becomes harder to ignore. The cloud expands differently. Interference patterns can appear. The particles respond collectively to changes in the trap. Separate atoms begin to share a single description. The next step is therefore not simply another reduction in temperature. It is a change in how matter must be understood, because once the quantum waves of neighbouring atoms overlap, the idea of each atom following its own private path no longer provides the full story. The idea of each atom following its own private path no longer provides the full story because quantum mechanics assigns wave-like behaviour to matter. This wave behaviour is always present, even in a warm gas, but ordinary thermal motion usually keeps it hidden. Cooling changes that. As atoms lose speed, the scale of their quantum waves grows, and the distance over which those waves matter becomes larger. A fast atom has a very short matter wavelength. Its wave behaviour varies over such a small distance that the atom often appears to behave like a tiny particle moving along a definite route. A slow atom has a longer wavelength. Once that wavelength becomes comparable to the spacing between atoms, neighbouring particles begin to affect one another in ways that cannot be explained by treating them as separate balls. This does not mean an atom stretches into a soft physical object in the ordinary sense. The wave describes the range of possible outcomes for measurements such as position and momentum. It also describes how different possibilities can combine, reinforce one another, or cancel. These effects are familiar in experiments with light. Send light through two narrow openings and a pattern of bright and dark bands can appear on a screen. Light travelling through the two openings behaves like overlapping waves. Where the waves reinforce one another, the screen becomes bright. Where they cancel, the screen becomes dark. Atoms can create similar interference patterns. A beam of atoms can be divided into different paths and later recombined. The final distribution contains bands that reveal wave interference. Each atom is detected as a localized event, but the pattern built from many detections follows wave behavior. At ordinary temperatures, atomic motion is too varied for these patterns to remain clear. Different atoms have different speeds and directions. Their quantum phases change at different rates. Any interference is quickly blurred. Cooling narrows the range of velocities. The atoms become more alike in their motion, and their matter waves can remain related for longer periods. This makes interference easier to observe and control. The change becomes especially important when many identical atoms occupy the same region. Quantum mechanics divides particles into two broad groups called bosons and fermions. The difference is not based on size, electric charge, or whether the particles seem friendly in laboratory photographs. It comes from their quantum properties and determines how identical particles may share states. Bosons are allowed to gather in the same quantum state. Many bosonic atoms can have the same energy, the same overall motion, and the same spatial wave pattern. Fermions follow a different rule. Identical fermions cannot all occupy exactly the same quantum state. Both types of behavior become much easier to see at low temperatures. Consider a gas of bosonic atoms in a trap. At first, the atoms occupy many different motional states. Some move quickly, some slowly, and their waves have little organized relationship. Evaporative cooling removes energetic atoms and allows the rest to settle into lower states. As the temperature falls, more atoms gather in the lowest available state. Once a critical condition is reached, a large fraction of the gas enters that state together. This sample forms a Bose-Einstein condensate. The name comes from Satyendra Nath Bose and Albert Einstein, who developed the statistical ideas that predicted this behavior. Bose first worked out a new way of describing particles of light. Einstein extended the reasoning to atoms and predicted that a gas could undergo a major change when cooled sufficiently. For many years, the prediction remained beyond experimental reach. The required temperatures were extremely low, and physicists had no practical way to cool and contain a suitable atomic gas. Laser cooling, magnetic trapping, optical trapping, and evaporative cooling eventually provided the necessary tools. When the first dilute atomic condensates were created, researchers were able to observe matter behaving collectively on a visible laboratory scale. Thousands or millions of atoms could be described by a shared matter wave. It is tempting to say that all the atoms merge into one giant atom. That is not quite correct. The particles remain atoms, and interactions between them still matter. What they share is a common quantum state. Their individual identities become less useful for describing the behavior of the sample. A crowd of people walking through a station usually moves in many directions at different speeds. A condensate is not simply a crowd that has agreed to walk slowly. It is closer to a group whose motion is governed by one shared pattern. The analogy remains limited because people do not become indistinguishable quantum particles, regardless of how similar their winter coats may be. One of the clearest ways to see the shared wave behavior is through interference. A condensate can be divided into two parts and then released. As the two clouds expand and overlap, they produce a pattern of alternating dense and sparse regions. This is matter wave interference. The pattern resembles interference produced by light or water waves, but the waves belong to atoms. Each atom is still detected at a particular location when the cloud is imaged. The complete pattern emerges from the distribution of many atoms. The result shows that the condensates carried coherent wave information before they overlapped. Coherence means that the phase relationships within the wave remain organized. A normal warm gas has little long-range coherence because the atoms move independently. A condensate can maintain a common phase over the size of the cloud. This allows physicists to perform forms of atom interferometry. They split an atomic wave, allow the parts to follow different paths, and then recombine them. Differences between the paths alter the interference pattern. Gravity can cause such a difference. Acceleration, rotation, magnetic fields, electric fields, and changes in time can also affect the paths. By reading the pattern, researchers can measure these influences with great sensitivity. Light interferometers have been used for precise measurements for a long time. Atom interferometers add new possibilities because atoms have mass and respond strongly to gravity and inertial motion. A cold atom interferometer can act as an accelerometer, a rotation sensor, or a gravity measuring device. It can detect small changes in the local gravitational field, which may be useful for geology, navigation, and tests of fundamental physics. The atoms must be cold because uncontrolled motion would wash out the phase information. A warm cloud expands too quickly and contains too many different velocities. A cold cloud provides a narrow, controlled source of matter waves. Bose-Einstein condensates can also display superfluid behavior. A superfluid flows with extremely low resistance under suitable conditions. It can move through narrow spaces and support circulating currents that persist for long periods. This does not mean every condensate automatically flows forever in every container. The behavior depends on interactions, trap geometry, temperature, and disturbances. Still, the gas can respond as a coherent fluid rather than a collection of independent particles. Rotation produces an especially clear quantum effect. In an ordinary liquid, circulation can vary continuously. In a superfluid, rotation can appear through quantized vortices. Each vortex is a small region around which the fluid circulates in a fixed quantum amount. When a trapped condensate is rotated, a regular array of vortices can form. Images of the cloud show small holes arranged in a pattern. The holes mark the vortex cores, where the density drops. The arrangement provides a direct view of quantum rules operating across a cloud much larger than a single atom. The same kind of quantized circulation appears in other systems, including liquid helium and superconducting materials. Cold atomic gases are useful because their conditions can be changed with great control. The strength of interactions can be adjusted. The trap can be made round, long, flat, or divided into separate regions. The number of atoms can be varied. Magnetic and optical fields can be applied in carefully timed sequences. This control lets researchers build simplified versions of complicated physical systems. An optical lattice is one example. Several laser beams overlap and form a repeating pattern of bright and dark regions. Depending on how the light is tuned, atoms are attracted to particular parts of the pattern. The result is a regular array of trapping sites. The arrangement resembles the repeating structure of atoms in a solid crystal, but it is made from light. Cold atoms placed in the lattice can move between sites, interact with neighbours, or become localized. By changing laser intensity, researchers control how easily atoms travel through the lattice. By changing interactions, they control how strongly atoms affect one another. This creates a flexible model for studying behavior that also appears in real materials. Electrons in solids are difficult to observe individually. They move through complex structures and interact through electric forces. Cold atoms in optical lattices allow similar mathematical problems to be explored in a cleaner and more adjustable setting. This approach is called quantum simulation. The cold atom system does not imitate every detail of a material. Instead, it reproduces selected rules so that their consequences can be measured. Researchers can study magnetism, phase transitions, transport, localization, and strongly interacting particles. They can change one condition at a time and observe how the behavior develops. The experiment may involve taking repeated images of the cloud after varying the lattice depth or interaction strength. In advanced systems, microscopes can detect individual atoms at individual lattice sites. These quantum gas microscopes give remarkably detailed views. They can show whether a site is occupied and how patterns change from one experimental run to another. The images do not photograph a tiny atom in the same way a camera photographs a chair. The atoms are detected through fluorescence or other controlled interactions with light. Even so, the result allows researchers to reconstruct the arrangement particle by particle. Fermionic atoms produce a different set of low-temperature effects. Because identical fermions cannot share the same quantum state, they fill available states from the lowest upward. Even near the lowest possible temperature, not every fermion can settle into the lowest energy state. Once one state is occupied, the next particle must use another. This creates a filled range of states known as a Fermi sea. The gas still has motion, even when ordinary thermal energy has become extremely small. That motion comes from the exclusion rule rather than heat. Electrons are fermions, so this principle is central to the behavior of metals, semiconductors, and many other materials. It also helps explain why matter remains stable. Electrons cannot all collapse into the same lowest state around an atomic nucleus. In dense stars called white dwarfs, pressure associated with fermionic particles helps resist gravitational collapse. Cold fermionic atoms provide a much gentler laboratory system for investigating related quantum statistics. Fermions can also form pairs. Two fermions together can behave as a bosonic object and occupy a shared state with other pairs. This pairing is important in superconductivity, where electrons move through a material without ordinary electrical resistance. Cold atom experiments can create paired fermionic gases and vary the interaction between particles. Under some conditions, the pairs are large and overlapping. Under others, they behave more like tightly bound molecules. By moving smoothly between these regimes, physicists study how different forms of pairing are connected. The laboratory system can be adjusted in ways that are difficult or impossible in solid materials. None of this behavior would remain clear if the atoms were warm. Thermal motion would break pairs, disturb coherence, populate many unwanted states, and hide the effects of quantum statistics. Cooling is therefore not merely a method for making the atoms easier to hold. It removes the ordinary motion that competes with quantum organization. The transition into a condensate also illustrates that temperature can change the form of matter without changing its chemical identity. Rubidium atoms remain rubidium atoms, sodium remains sodium. The new behavior comes from how the particles occupy quantum states. This resembles familiar phase changes in one limited sense. Water can become solid, liquid, or gas depending on temperature and pressure. The molecules remain water molecules while their collective organization changes. The Bose-Einstein condensate is not simply a very cold solid or liquid. It is a distinct quantum state, created when many bosons occupy a shared state. The shape of a condensate is influenced by the trap and by interactions between atoms. If the atoms repel one another, the cloud spreads more than a non-interacting gas would. If they attract too strongly, the condensate can become unstable and collapse. Magnetic fields can often be used to tune these interactions. Researchers can gradually increase attraction and observe the cloud shrink. Under certain conditions, it collapses and ejects atoms in a sudden burst. These experiments reveal how a simple quantum system responds when the balance between confinement, kinetic behavior, and interaction changes. Condensates can also support sound waves. A small disturbance travels through the cloud as a collective change in density. Measuring its speed provides information about interactions and compressibility. Other excitations can be created by shaking the trap, changing its shape, or applying pulses of light. The cloud may oscillate, expand, divide, or develop waves along its surface. Because the system is cold and controlled, these responses can be compared closely with theoretical models. Measurement still presents a difficulty. Quantum systems are disturbed when observed. Imaging often requires scattering photons, which heats or destroys the sample. Many experiments therefore prepare the cloud, apply a controlled sequence, and then take a final image. The same procedure is repeated to examine another time or setting. A film of the process may actually be assembled from many separate clouds. Each image shows a different experimental run stopped at a different moment. The atoms used for the first frame are not the atoms used for the next. This can make cold atom research seem wasteful, since every measurement may release or destroy a carefully prepared sample. Fortunately, the samples contain very little material. The greater cost is time, equipment, and the patience needed to reproduce nearly identical conditions. Cold atom experiments also provide tests of quantum mechanics itself. Interference can be measured over increasing distances and durations. Atomic clocks can compare the passage of time at different heights. Matter waves can test whether gravity affects different atoms in the same way. Researchers search for tiny deviations from established predictions. So far, quantum mechanics and relativity have survived many precise tests, but higher accuracy may reveal new effects or place stronger limits on alternative theories. Antimatter atoms can also be cooled and studied, though this is much more difficult. Antihydrogen consists of an antiproton and a positron. It must be produced, trapped, and protected from contact with ordinary matter. Cooling antihydrogen allows more precise comparisons with hydrogen. Scientists can examine whether matter and antimatter have exactly matching spectral properties and how antimatter responds to gravity. These experiments use some of the same broad ideas developed for ordinary atoms, including magnetic trapping and laser cooling. The number of available anti-atoms is small, and every trapped particle is valuable. Quantum wave behavior is not restricted to specially chosen laboratory atoms. All matter has it. A person, a table, and a sleeping cat also have quantum descriptions. For large warm objects, interaction with the environment destroys observable coherence extremely quickly. Air molecules collide with them. Thermal radiation is emitted and absorbed. Internal particles interact in countless ways. Information about different quantum possibilities spreads into the surroundings. This process is called decoherence. It explains why large objects usually appear to follow ordinary classical behavior even though their components obey quantum mechanics. Cold atoms are isolated from many of these environmental disturbances. The vacuum reduces collisions. Low temperature reduces random motion. Carefully controlled fields replace uncontrolled surroundings. Isolation allows quantum coherence to survive long enough to measure. Perfect isolation is neither possible nor always useful. The atoms must eventually be prepared, controlled, and detected, all of which require interaction. The art lies in choosing which interactions occur and when. A laser pulse may create a superposition of two internal states. A magnetic field may allow those states to develop differently. Another pulse recombines them. A final measurement converts the phase difference into a detectable population. This sequence forms the basis of many atomic sensors and clocks. An atomic clock uses a transition between two internal states as a reference. Cold atoms spend longer interacting with the probing light and experience smaller motion-related shifts. Optical lattice clocks hold atoms in place while measuring transitions at frequencies associated with visible or near-visible light. These clocks can become so sensitive that a small change in height affects the measured rate through gravitational time dilation. Moving a clock upward by a modest distance changes its relationship with Earth's gravity by an amount that advanced instruments can detect. The measurement connects several ideas that began with cooling. Light slows the atoms, traps hold them. Quantum coherence creates a precise frequency reference. Relativity changes the passage of time. A laboratory device then reads that change. Cold atoms also support new approaches to navigation. An atom interferometer can measure acceleration without relying on signals from satellites. In environments where satellite navigation is unavailable or unreliable, such sensors may provide an independent reference. Building a practical device is difficult. Laboratory systems are large and sensitive. Lasers must remain stable. Vibrations must be controlled. The vacuum chamber and electronics must operate outside ideal conditions. Engineers are working to make these systems smaller and more robust. The physics that once required an entire optical table can sometimes be packaged into more compact instruments, though the atoms continue to demand careful treatment. Quantum technologies may also use individual neutral atoms as information carriers. Optical tweezers can trap atoms one by one using tightly focused laser beams. Arrays of traps can arrange them into chosen patterns. The internal states of the atoms can represent quantum information. Laser pulses control interactions between selected atoms. Because neutral atoms are naturally identical, each one begins with the same basic properties. Cooling is necessary so that the atoms remain inside the tiny traps and respond predictably. Excess motion would blur the laser control and cause particles to escape. These arrays are being explored for quantum computing and quantum simulation. They offer a way to create large, reconfigurable systems of controlled particles. The atoms may be arranged in rows, squares, rings, or more complicated shapes. Optical systems move the tweezers and fill empty sites. The final pattern can contain hundreds or more controlled atoms. Once again, the same light that might ordinarily heat matter becomes a tool for slowing, holding, arranging, and controlling it. The development from a warm atomic vapor to a quantum wave system is not a single dramatic step. It is a sequence of careful reductions in uncertainty and motion. Fast atoms are selected, their forward speed is reduced, opposing beams damp random velocity, magnetic fields gather them into a cloud. Further cooling narrows the motion. Evaporation removes the energetic particles. Traps isolate what remains. At the end of this sequence, behavior that was always present becomes visible. The atoms interfere because matter has wave properties. Bosons gather because their quantum statistics allow it. Fermions fill different states because their statistics require it. Coherence persists because environmental disturbances have been reduced. Cooling does not add quantum mechanics to the atoms. It removes the conditions that were hiding it. That is why cold atom research has become important across so many areas of physics. It offers clean matter waves for sensors, stable particles for clocks, adjustable gases for studying many body systems, individual atoms for quantum information, and controlled tests of basic physical laws. The cloud in the vacuum chamber may contain only a tiny amount of matter, but it can reproduce behavior connected to solids, superfluids, superconductors, dense stars, and the early universe. These connections do not mean a cold gas is identical to every system it models. The value lies in creating selected rules under conditions that can be measured and changed. A material may contain defects that cannot be removed. A cold atom lattice can be built with chosen patterns of disorder. A solid may have interactions fixed by chemistry. Atomic interactions can often be tuned with magnetic fields. A condensed matter experiment may hide individual particles. A quantum gas microscope can reveal them site by site. This control turns cold atoms into a general laboratory for quantum behavior. The original question was why light can cool atoms instead of heating them. The answer began with momentum and selective absorption. It then grew into Doppler shifts, optical molasses, magnetic trapping, sub-Doppler methods, and evaporative cooling. At the lowest temperatures, the purpose of cooling becomes clearer. The goal is not simply to produce a very small temperature reading. The goal is to prepare matter so that subtle effects can be observed without being overwhelmed by random motion. Once that happens, atoms become precise clocks, sensitive accelerometers, coherent waves, model materials, and controllable quantum units. The next question is what these abilities change outside the cooling experiment itself, because holding a quiet cloud in a vacuum chamber would be an impressive technical achievement even if it led nowhere else. In practice, the methods developed to cool atoms have changed how time is measured, how gravity is tested, how quantum matter is studied, and how new technologies are being designed. In practice, the methods developed to cool atoms have changed how time is measured, how gravity is tested, how quantum matter is studied, and how new technologies are being designed. The importance of cold atoms does not come from temperature alone. It comes from what becomes possible once random motion is reduced, and individual particles can be controlled for long enough to reveal small effects. A warm atom moves quickly through an experiment. It sees light shifted by its motion, collides with other particles, and leaves the observation region almost immediately. A cold atom remains available. It can interact with a laser for longer, follow a carefully arranged path, or sit inside a trap while researchers make repeated measurements. This increased control changes the precision of the experiment. A small effect that would be hidden inside the motion of a warm gas can become measurable in a cold one. The atom has not gained a new property. The disturbances around that property have become smaller. Atomic clocks are one of the clearest examples. Every atom of a particular type has the same set of internal energy transitions. A clock can use one of those transitions as a frequency reference. Rather than depending on a swinging pendulum or a vibrating quartz crystal, it counts an extremely regular atomic process. Warm atoms make this difficult because they move in different directions at different speeds. Their motion changes the frequency of the light they experience through the Doppler effect. The transition appears broadened, and the center becomes harder to identify precisely. Cooling reduces that motion. The atoms interact with the clock laser for longer and respond within a narrower range of frequencies. The clock can then determine the transition frequency with greater accuracy. Some modern atomic clocks use atoms held in optical lattices. The lattice is formed by overlapping laser beams that create a repeating pattern of trapping locations. Each atom is held in place while another laser probes its internal transition. The trapping light is chosen carefully so that it affects the two clock states in nearly the same way. This reduces errors that would otherwise come from the trap itself. The atoms remain confined, their motion is small, and the measurement can continue for a relatively long time. The result is a clock so precise that gravity becomes relevant over ordinary height differences. General relativity tells us that time passes slightly more slowly in stronger gravity. A clock closer to Earth runs at a different rate from an identical clock positioned higher above the surface. The difference is tiny, but advanced atomic clocks can detect it. Raising one clock by a small distance can change its measured rate, enough to observe under controlled conditions. This does not mean someone on the upper floor of a building returns from lunch noticeably older than a colleague downstairs. The effect is far too small for that. It does mean that cold atom clocks can turn a prediction about curved space-time into a laboratory measurement. They can also act as tools for studying the shape of Earth's gravitational field. Since clock rates depend on gravitational potential, comparing precise clocks at different locations can reveal differences in height and mass distribution. This approach may eventually support new forms of surveying. Traditional height measurements rely on reference points, satellite observations, and models of Earth's shape. Clock comparisons could provide another method based directly on relativity. Cold atoms also improve measurements of gravity through atom interferometry. In these experiments, laser pulses divide an atomic matter wave into different paths. The paths travel through slightly different regions before being brought back together. Gravity changes the motion and phase along each path. When the waves recombine, the interference signal contains information about the gravitational acceleration. Because the atoms are cold, their initial speeds are well controlled. The paths can be kept coherent, and the resulting phase difference can be measured precisely. Such instruments can detect small variations in gravity from place to place. These variations may be caused by underground structures, changes in water levels, geological formations, or nearby masses. A gravity sensor does not take a photograph of what lies underground. It measures how strongly nearby mass affects the atoms. Researchers then interpret those measurements using physical models. This could support the search for underground cavities, the monitoring of volcanic activity, or the study of changes in groundwater. Practical field instruments must become compact, stable, and resistant to vibration, but the underlying measurement has already been demonstrated in laboratories. Atom interferometers can also measure acceleration and rotation. That makes them interesting for navigation. Most modern navigation systems rely heavily on satellite signals. A receiver determines its position by comparing carefully timed signals from several satellites. If those signals are unavailable, blocked, or unreliable, another reference is needed. An inertial navigation system measures how an object accelerates and rotates, then uses that information to estimate changes in position. Conventional inertial sensors gradually accumulate errors. Even a small measurement mistake can grow over time. Cold atom sensors may provide more stable references. Matter wave interference can reveal acceleration with high precision. A practical system might combine atomic sensors with conventional devices, using each to correct the weaknesses of the other. The difficulty is that laboratory atom interferometers often require vacuum chambers, lasers, magnetic shielding, vibration control, and carefully timed electronics. A ship, aircraft, or vehicle is not as calm as an optical table. Movement, temperature changes, and mechanical vibration can disturb the measurement. Turning a precise experiment into a dependable machine is a separate challenge from proving that the physics works. Even so, the history of technology contains many systems that began as large laboratory arrangements. Early atomic clocks filled substantial rooms. Lasers once required equipment that would not have fitted comfortably into an ordinary device. Development gradually made them smaller and more reliable. Cold atoms also allow more accurate measurements of physical constants. A physical constant is a value that appears throughout the laws of nature, such as the strength of certain interactions or the relationship between energy and frequency. Measuring these values tests whether different parts of physics agree. If separate methods produce conflicting results after every known error has been removed, that could point to missing physics. Cold atom experiments can measure the recoil an atom receives when it absorbs a photon. Since the momentum of the photon and the mass of the atom are known or can be related to other quantities, the recoil provides access to fundamental constants. The atoms must be cold because the recoil from a single photon is small. In a warm gas, it would be hidden by the much larger spread of ordinary velocities. In a cold sample, researchers can track the accumulated effect of many controlled photon transfers. Precision measurements can also test whether constants change over time or vary between locations. Current evidence places strong limits on such changes, but improved clocks and sensors continue to make the tests more sensitive. Cold atoms provide another way to examine the equivalence principle, which states that different objects fall in the same way when other forces are removed. This principle is central to general relativity. Researchers can prepare two different atomic species, release them together, and compare their acceleration in gravity. If the atoms fall differently after all known effects are accounted for, the result would challenge a major part of modern physics. No confirmed violation has been found in such experiments. Their absence is still informative. Each improved measurement reduces the range in which an unknown effect could be hiding. This is common in precision physics. A result does not need to reveal a new particle or a broken law to matter. Showing that a theory remains correct to a greater level of accuracy changes what future theories are allowed to predict. Cold atoms are also used to test quantum mechanics at larger scales and over longer times. Quantum theory has passed every reliable experimental test so far, but researchers continue to examine whether it remains complete under new conditions. Matter-wave interference can be performed with atoms, molecules, and increasingly complex systems. As the objects become larger, keeping them isolated becomes harder. Collisions, thermal radiation, and internal motion destroy coherence. Cold atomic systems provide a clean starting point because their environment is controlled and their motion is small. Researchers can deliberately add noise or interactions and watch coherence disappear. This helps them study the boundary between quantum behavior and ordinary classical behavior. There may not be a single sharp boundary. Instead, classical behavior can emerge as quantum information spreads into the environment through decoherence. Understanding this process matters for quantum technologies. A quantum sensor or computer depends on preserving controlled superpositions. Any unwanted interaction can damage the information. Neutral atoms are becoming an important platform for quantum computing. Individual atoms can be captured in optical tweezers, which are tightly focused beams of light that create tiny traps. A camera detects which traps contain atoms. Empty sites can be filled by moving trapped atoms into a desired arrangement. The result is an ordered array built one particle at a time. Each atom can store quantum information in selected internal states. Laser pulses prepare those states, change them, and measure them. Interactions between nearby atoms allow operations involving more than one quantum unit. One useful method excites atoms into highly energetic states known as Rydberg states. In these states, the outer electron is far from the nucleus, and the atom interacts strongly with nearby atoms. If one atom is excited, it can prevent another nearby atom from being excited in the same way. This effect allows conditional operations needed for quantum computing and simulation. The atoms must remain cold so that they stay inside the optical tweezers and maintain predictable positions. If they move too much, the laser pulses no longer address them consistently, and the strength of interactions changes. Cooling therefore supports both the storage and processing of quantum information. The same photon momentum that first slowed the atoms becomes part of a larger system for arranging and controlling them. Cold atom arrays can also simulate models of magnetism. The two internal states of each atom may represent two possible directions of a tiny magnetic unit. Interactions between atoms then reproduce rules similar to those used to describe magnetic materials. Researchers can prepare an initial pattern and observe how it develops. They can change the arrangement of atoms, the strength of interactions, or the timing of the controls. These experiments help investigate systems that are difficult to calculate on ordinary computers. The problem is not that the physical rules are unknown. It is that the number of possible quantum configurations grows extremely quickly as more particles are added. A controlled quantum system can perform the evolution naturally. Scientists then measure the outcome and compare it with theoretical predictions. Other cold atom simulators place particles in optical lattices. The atoms move through a repeating structure created by light, much as electrons move through the repeating structure of a crystal. The strength of the lattice controls how easily atoms move between sites. Magnetic fields control their interactions. Lasers can create artificial forces that act like electric or magnetic fields, even though the atoms themselves may be electrically neutral. This allows researchers to study transport, insulating behavior, magnetism, and unusual phases of matter. One important transition occurs between a superfluid and a Mott insulator. In the superfluid state, atoms spread coherently across the lattice and move easily. In the insulating state, strong interactions pin a fixed number of atoms to individual sites. The atoms have not become ordinary solid objects. The change comes from the competition between their tendency to move and the energy cost of occupying the same site. By increasing the lattice depth or interaction strength, researchers can move the system through this transition and observe how coherence disappears. Quantum gas microscopes can then image the atoms site by site. What was once a theoretical model of particles on a grid becomes a visible pattern of occupation in a controlled experiment. Cold gases also help study superconductivity and superfluidity. Fermionic atoms can pair, and those pairs can move coherently. The interaction strength can be tuned with magnetic fields. Researchers can explore the transition from large overlapping pairs to tightly bound molecular pairs. This gives them a controlled system for studying pairing behavior related to superconductors. It does not reproduce every feature of a real material, but it isolates important parts of the problem. The same systems can help physicists investigate matter under conditions that are difficult to create elsewhere. Strongly interacting atomic gases may share mathematical properties with nuclear matter or matter inside dense stars. No one is claiming that a small cloud of lithium atoms is literally a neutron star. The value lies in common relationships between pressure, density, interactions, and quantum statistics. If two systems follow similar equations under certain conditions, a controllable one can provide information about the less accessible one. Cold atoms have also become useful in the study of chemistry. At ordinary temperatures, chemical reactions involve many collision speeds, rotational states, and vibrational states. The range of possibilities makes detailed control difficult. At ultra-low temperatures, only a small number of collision pathways remain available. Quantum effects can determine whether particles react, scatter, or form molecules. Researchers can prepare atoms or molecules in selected internal states and observe individual reaction processes. External fields can alter the probability of a reaction. This creates the possibility of controlled quantum chemistry, where the initial conditions are specified much more precisely than in an ordinary container. Ultra-cold molecules are especially promising because they can interact through electric dipoles. Those interactions are long-range and directional, making them useful for quantum simulation and information processing. Molecules are harder to cool than atoms because they contain many more internal states. A molecule can absorb light and then release it into a different rotational or vibrational state, leaving the cooling cycle. New laser cooling schemes use carefully chosen molecules and several repumping frequencies to keep them participating. Other methods assemble cold molecules from atoms that have already been cooled. These developments show that the original idea of using light to slow an atom has expanded far beyond its first applications. Cooling also changes our understanding of temperature itself. In daily life, temperature is associated with touch and comfort. A cold object draws heat from the skin. A warm object transfers heat into it. A cold atomic gas may contain so little material that touching it would be impossible and meaningless. The temperature describes the narrow spread of particle motion, not a sensation available to a human hand. The atoms can be far colder than the surrounding chamber without freezing the walls. Temperature is a property of the selected system and its distribution of energy. This reminds us that familiar words can have more precise meanings in physics. Cold does not always mean covered in frost. A trap does not need solid walls. A wave does not require water. Pressure can come from light. A cloud can contain only a tiny number of particles. The language begins with everyday experience, but experiments force it to become more exact. Laser cooling also changes the usual division between light and matter. Light is often treated as something that allows us to see matter. In cold atom laboratories, light is an active mechanical tool. It pushes atoms, slows them, traps them, arranges them, changes their internal states, and measures the results. Different laser beams can perform different jobs within the same experiment. One beam may cool, another repumps, another forms a trap, another drives a clock transition, another produces an image. The atoms respond differently because each beam has its own frequency, polarization, direction, and timing. A laboratory that looks like a collection of mirrors and cables is really a system for delivering precise instructions through light. The success of laser cooling also demonstrates the importance of small repeated effects. One photon does very little to an atom. Millions of controlled interactions transform the sample. Scientific progress often works the same way. A single improvement in frequency stability, vacuum pressure, detector sensitivity, or magnetic control may seem minor. Combined with many others, it opens a new range of experiments. The first demonstrations of atomic slowing did not immediately produce quantum computers or clocks sensitive to height. They established control over motion. Later work added trapping, subdoppler cooling, evaporation, optical lattices, and single-particle imaging. Each technique became a tool used to build the next one. There are still limits and unanswered questions. Cooling systems lose atoms. Lasers introduce noise. Traps disturb energy levels. Measurements destroy samples. quantum coherence remains fragile. Practical devices must work outside carefully protected laboratories. They must survive vibration, changing temperatures, and long periods of operation without constant adjustment. Researchers are developing smaller vacuum systems, compact lasers, integrated optical components, and automated controls. These efforts may allow cold atom instruments to move from specialist laboratories into observatories, vehicles, communication systems, and surveying equipment. Some applications will succeed. Others may remain too complex or expensive. Scientific importance does not depend entirely on commercial use. Cold atoms already provide a way to ask questions that could not be tested before. How accurately do different objects fall? How stable are the constants of nature? How does a quantum system become classical? How do many interacting particles organize themselves? How precisely can time be measured? The answers affect our view of the universe because they test the rules used to describe everything from laboratory particles to stars and galaxies. A clock based on a trapped atom connects quantum mechanics with relativity. An atom interferometer connects matter waves with gravity. A quantum simulator connects a small gas with complex materials. A condensate connects individual particles with collective behavior. The experiments are small, but the principles are not. We began with an apparent contradiction. Light usually warms matter, yet it can cool atoms. The contradiction disappeared once we looked at the details. Light carries momentum. Atoms absorb only selected frequencies. Motion changes the frequency an atom experiences. A carefully tuned beam pushes more strongly against atoms moving toward it. Opposing beams reduce motion from every direction. Magnetic fields add confinement. More advanced methods remove the motion that remains. As the atoms become colder, quantum behavior becomes visible. Their matter waves overlap. Bosons gather into shared states. Fermions fill distinct states. Interference turns gravity and acceleration into measurable phase changes. Cooling is therefore not the final goal. It is the preparation that allows nature to be examined with less interference from random motion. The next time sunlight warms a window or a lamp makes a room feel slightly hotter, it is still correct to think of light as carrying energy into matter. That familiar effect has not gone away. The cold atom experiment uses a more selective interaction. It does not shine ordinary light on ordinary material and expect the temperature to fall. It chooses an atomic transition, a laser frequency, a direction, a polarization, and a sequence. It makes the atoms that are moving in the wrong direction absorb the photons most likely to slow them. The result is not a violation of common sense. It is a reminder that common sense describes common conditions. Atoms in a vacuum chamber illuminated by carefully tuned lasers are not living under common conditions. They are showing us what the rules of physics can do when every detail is controlled. And now, as our journey through cold light comes to an end, you may be a little farther into the evening than when we began. Perhaps the room has cooled slightly on its own, without any lasers, magnetic coils, or emergency repumping beams. We have followed a photon as it pushed an atom, watched the Doppler effect select moving particles, entered optical molasses, added magnetic traps, moved below the Doppler limit, and reached gases that behave as coherent quantum waves. All of it began with a very small push. If you found this explanation useful, calming, or simply an agreeable way to spend some time with the atoms that move more slowly than most laboratory schedules, you can leave a like and subscribe to Physics with William. It helps this quiet part of the internet reach other people who may also enjoy science without alarms, countdowns, or someone insisting that the universe must be understood before breakfast. For now, the lasers can be switched off, the magnetic fields can settle, and the atoms can continue their small controlled movements in the dark chamber. Wherever you're listening from, and whatever the temperature may be in your part of the world, I hope the room feels comfortable and your thoughts are moving a little more slowly than they were before. Sleep well, fellow traveller.